Raghu, am I?
Yes, sir. But I think your connection is poor. Your voice is breaking, sir. Your voice is
Yeah,
breaking.
Raghu, am I audible now?
Your voice is breaking,
Hello?
sir.
Voice is breaking. Yeah, now?
Yes, sir.
Is it okay now?
Yes,
Okay.
Hello?
It's okay, sir. You can proceed.
Yeah. Raghu,
Sir.
okay, so that video is ready with you?
1 minute.
Video and photos, if you are ready with that, we'll present that and we'll go to the first presentation.
Yeah.
Yeah. So, my dear participants, good evening once again to all of you. Just we have two beautiful sessions today. Before starting the sessions, let us play a small video regarding to show about a disaster, what is happening. Okay, what has happened, please. Okay, Raghu, please.
Yeah.
This is the disaster landslide near Uttarakhand.
Raghu sir,
Yogi.
there is an echo from your side.
Echo.
नदीपुरी डाली अब कहाँ खुलता है फिर यार रोड खुलता है अब
Okay sir, okay, now it's okay.
देखो ना वो नीचे देखो नदी को बराबर हो गया ये नदी पूरी डाली अब कहाँ खुलता है फिर यार रोड खुलता है अब बेटा रोड भी गया नीचे आज तो शाम तक भी मुश्किल है रोड तो गया पूरा नीचे रोड गया नीचे और नदी
Just show that photos also. Two photos I have sent, no? Yeah, my dear participants, the earlier one which was happened in Uttarakhand, and the photo which we are showing is pertaining to the photos at Sikkim, where due to landslides and all this disaster has happened. Why we are showing is we the civil engineers have a lot of responsibility towards shaping up, even though it's a natural disasters, but the responsibility of us, because we are the one who has to give the suggestions and see. Yesterday also we have seen beautiful lectures regarding the how to counter this disaster. Okay, so now Raghu, Jitendra is there. Shall we start the session?
Yes, I am there, sir. Yeah. Good evening. Yes.
Yeah, thank you. Thank you. Good evening, Jitendra. Yeah. My dear participants, good evening once again to all of you. So today we have two sessions. So the first session is given by Sri Jitendra. So I am proud to say Jitendra was the alumni of our college and is our student. He did his BTech Civil Engineering from JNTU College of Engineering, Anantapur in 2012. He is All India 12th ranker in GATE examination. He's a proud student. That is the best rank in our college. Almost this 3 decades. That is the best rank I can say. He's a proud student of JNTU Anantapur. Later on, he did his MTech Structural Engineering from IIT Bombay. He currently lives in Hyderabad and works as senior engineer, mobility structures at Arcades, India. He's having over 10 years of experience in the conceptual and detailed design of various types of structures, including composite steel bridges, steel-plated box girder bridges, arch bridges, cable-stayed bridges, natural dot cooling towers, RCC steel frame structures, and liquid retaining structures. I hope today is going to present a topic on bridge resilient against natural hazards. My dear student participants, is having good exposure towards bridge engineering and is guiding our MTech students also. So thank you, Jitendra, for sparing your valuable time. And even though it's a Christmas, yeah, Merry Christmas to all of you. Now I hand over mic to Jitendra. Please carry on.
Thank you, sir. Thank you. So before I start, Merry Christmas to all of you and wish you a Happy New Year. And it's great to see so many doctors in the participants, and that I'm at the same time, I'm encouraged and also a little bit intimidated because I am not a doctor myself. So I spent after my MTech 10 years, as I said, designing bridges and various structures. So the range of structures is wide, a few bridges among them. So I'll try to give you a brief outlook or overview of how disaster disaster is a big term, and natural hazards, these are big terms. So what we try to do as engineers is try to use these mathematical models and then convert it into loads, and then use these loads, and also try to prevent some of the common failures by way of design, which is called eliminating risk by design. So I'll share some of the things that we have been doing and some of the things that I think we should do, what we are not doing. This kind of information I'll share. And also one more thing is that I am benefited in another way, that my master's thesis was also related to this field. The topic of my MTech thesis was earthquake hazard modeling. So I hope I am clear. The audio is clear, right?
Yes.
Yeah,
Yes,
okay. Okay, thanks. Because somebody else is raising hands, so I thought I'm not clear. Okay, fine. So my MTech thesis was also on source modeling. They call hazard modeling of seismic sources, and so I'm going to share some of that information today on how we design bridges for in these areas. And because many of you are either in PhDs or in academic field, I'm sure some of you must be already working on some of the areas that I'm going to talk about. And if you are working in these areas and know a little bit more information, please feel free to contribute and share. So I'm sharing my screen. Yes, you can see the presentation, right?
Yeah.
Okay, I'll start this presentation. So Welcome again. Happy Christmas. Merry Christmas. The topic today is bridges, resilience against natural hazards. So uh, I'll go through the index, and in the first page itself, you can see a nice RCC spandrel arch bridge. Of course, not designed by me. I never got to design any spandrel arch RCC bridge, but you can see here that the risk that the bridge is at, it is close by a sea, and then between two gorges, kind of a valley in between, and then anything can happen, flooding, cyclones or earthquakes, anything can happen. And it is very important that this bridge is remains in service, because it also looks like it is a bridge of deep importance, because it looks to be connecting to different, even towns, which there may not be any other road. So it is particularly important that these kind of bridges are resilient against these hazards. So by resilience, first we need to understand that it's not that the bridge should not have any damage. Bridge can have and will have damage. You cannot design a bridge to be withstanding everything. But the thing is, the damage should be controlled. The damage should be limited, and the damage should be such that within a short time we should be able to repair and get it back to its full strength. That's what we'll be talking about today. And the index is this. These are topics that I'll go through one by one. I'll just introduce what resilience means when it comes to bridges, because you might have already seen some discussion on resilience and disaster, hazards over the last 2 days. So, and I'll then go back to bridges, changing hazard scenario. I'll get to that in a bit, what I mean by changing hazard scenario. And then I'll explain how we design bridges for this kind of events, such as flood, cyclones, heat or fire, and also design for earthquakes. And then I'll touch upon multi-hazard scenarios, because more often than not, the hazard is not one. An earthquake comes, and then there is tsunami, and then flooding, all kinds of things happen together, or within short periods of time, that the bridge does not have enough time to recover. So we need to there are a lot of research going on, a lot more to be done, not yet fully established field. And then I'll conclude. So to start with, so you already might have known the resilience, the definition of resilience, because this is I believe the 5th session. So the definition is that it is the capacity to withstand and recover from the effects of a hazard. So it has got two different words in it. One is withstand and then recover. So you can see a graph here, which also you might have seen before. It is that on the x-axis there is a time, service life, and on the y-axis it is a performance. So the performance could be as simple as live load carrying capacity, or the deflection capacity, whatever it is. Let's take it as a live load carrying capacity, because that's what we want from the bridges. So you can see that at the start it has got some capacity, and it is already going downwards, because as the time increases, that the structure would be aging. So aging includes degradation of material properties, and also civil engineering students might know creep and shrinkage, because of which the capacity of the sections get reduced, or so. And then there will be a disaster happening, kind of, let's say an earthquake happens. And when earthquake happens, obviously the bridge is going to take some of the damage. And then the idea is that the potential or the performance that it is lost due to the disaster is so much, and the balance, whatever is left, is called reliability, which means that the bridge can definitely survive this earthquake. So what we want is that at this position, the bridge is good enough that it doesn't collapse. It is good enough for emergency services, good enough for rescue operations, etc., to be taken care of. And then we start repairing it, and it is called recovery path. That's why. And once the recovery is done, the target is that the bridge is going back to its original state, and then serve the rest of its life. So therefore the resilience is a combination of these two, reliability and also recovery, not just reliability. So I'll show you a flow chart. So in this flow chart, we can see that the resilience of a bridge, this is particularly relevant to bridges. Resilience of a bridge is being shown in two different subcategories, where reliability is all these things, foundation, abutment. For example, if a foundation is damaged, pretty much the bridge is not serviceable. You cannot use that bridge even for the rescue operations. So there are some things that are absolutely necessary for the bridge to be safe during earthquakes. So that is why we are putting all these things in the reliable categories. You can see the main girders, in-span joints, which means if it is a continuous bridge, there are joints at above the pier, and also splices wherever the splices are there. So this kind of geometry, the bridge cannot afford to miss its geometry, the alignment change during disasters, etc. So the reliability is important part, and then comes recovery. So recovery is also equally important, and to be able to have the recovery in shortest possible time and to reach the original design intent of the bridge, we need to be doing this kind of operations, which are structural monitoring is continuous and non-invasive, I mean non-destructive, continuous observance of the bridge, and then maintenance of the bridge, because bridge has got many components. Some need maintenance, some don't need maintenance. So the regular maintenance, and also the degree of damage, structural importance, because naturally bridges, as you know, are lifeline, so they cannot be shut down during important periods. And also availability of resources. Availability of resources is one of the key things that we need to be aware of, because once, let's say, an earthquake comes and the bridge suffers some damage, and you need the bridge to be back up as soon as possible. Now you cannot be having the bridge original materials that are not available nearby or not immediately procurable. For example, just an example, let's say a cable stayed bridge is there in our state, and there is some earthquake, some cyclone or whatever, and some of the cables got damaged. So you know that when the cables are damaged, cables have snapped, the bridge is no more able to take the load. And guess what, no cables are being manufactured in India. So then you have to go to either China or Singapore, Hong Kong, these kind of places, and then get the cable manufactured to exact cut lengths and brought them through customs, and then install on the bridge. So that is all time lost if that is the situation. And if your bridge doesn't function during that time, the bridge is not resilient. So you need to have either locally supplied materials, or you need to, there are different ways. You need to design the bridge in such a way that loss of one or two cables is okay. Like the bridge, with some traffic restrictions, with some speed restrictions, etc., the bridge remains in service with one or two loss of cables in such cases. So that is the kind of design we're talking about, resilience. And also approachability. We have seen just a while a video, and there has been a landslide, and pretty much the whatever is on the other side is not approachable. So that kind of bridge is not resilient, the route is not resilient. So it is important to note all these aspects when we are talking about resilient infrastructure, and particular resilient bridges, right? And to note the video that Raghu was showing, it is kind of surprising, like not just the collapse is the landslide is not surprising. It happens all the time in our country, but look how close people are going, without having any awareness of the risk that is involved. Because there is no reason why the landmass that they are standing should not collapse, right? Right when there is a slip circle formed just before, beside them, obviously there is going to be another one formed there. So you need a certain awareness to be acting in this kind of areas. Anyway, so I'll go to common hazards in India. This is national, I think it is NDMA, not NMDA, National Disaster Management Authority. And it has given a list of hazards, because they are supposed to do the rescue relief operations after all of these events. So you can see that earthquakes, floods, heavy rainfalls, cyclones and storms. Storms maybe cyclone is also one of the one, and also hailstorms, these kind of things, and urban flooding, fires, heat waves, cold waves, snow and avalanches, and landslides, and the one that we have seen before, droughts, tsunamis, and some biological disasters. These are all the hazards that we have in our country. And out of these, I noted down that some of them are extreme weather events, are particularly related to weather. So they are obviously influenced by climate change. You know that the climate change is happening at a pace worse than ever before. So all these things are going to be affected by climate change. And you already know, I think by intuition, without being shown a data, that the temperatures are getting worse, the rainfall is getting worse every year. So there is some visible change in the patterns, in the frequency of these extreme weather events because of climate change. So and the bracket that shown here on the right side is the hazard that where there is direct relevance to bridge infrastructure. And we'll see some of the extreme weather events. Okay, first of all, heavy floods, heavy rains, floods and landslides. In India, IMD categorizes that if the rainfall is more than 64 millimeters in 24 hours, that is called heavy rainfall. And if it is 64 to 115, heavy rainfall, 115 to 204 millimeters, very heavy, and above 204, extreme rainfall. And then cloudburst is over a localized area accompanied by strong wind and lightning. And then lightnings and storms, they are electrical discharges, they're always there. And storms include dust storms, hailstorms, thunderstorms, and gales. Gales are the very strong winds which you see in cyclones. Cyclones are nothing but these intense vortex, wheels of low pressure area around which there is a very strong wind circulating. And then there are heat waves and cold waves. So initially, it may not look like they are going to affect bridges, but there are some subtle effects of them on bridges. I'm hearing some sounds. If there is anything, please let me know, because I cannot see anything on screen. Okay. And cold waves and hot waves. Okay. And also snowfall. So snowfall is also a hydrological hazard similar to rainfall, and a large amount of snow can affect the transport, crops and people. Out of these, the main point that we want to discuss is the effect of climate change. You can see, if you see these two, what you call histograms, on the left one, it is the frequency. On the right one, it is flood. So frequency is kind of in a year, what is the number of instances you have for floods, heat waves, droughts. This is within country, not in a year, the total. The 1998 to 2019. You can see the number of floods. On the right side is more defining image. Is that you can see from 1998 to 2008, 2010 to 2019, the frequency is gradually increasing. Even though there is ups and downs, but the average or the mean, you would say, seems definitely increasing. And there are, even after 2019, the data stops here at 2019, but in the last 5 years also, there have been many cases where the occurrence of extreme weather events are more than 6 and 8. So you would imagine that just 25 years ago, we are dealing with a climatic situation where we are expecting one storm, one cyclone, or one earthquake, this kind of things, cloudburst, 1 or 2 at best. And now we are dealing with 10 at a time, dozen at a time, and it is definitely important that our our bridges survive this. And not only that, if there are 10 extreme events in 2018, that means that there is an earthquake, there is a cyclone, probably there is a heat wave, all of them at the same location maybe. So it is very important to be able to imagine or discuss about how bridges behave in this kind of environment. And the pattern is not just from 1998 to 2019. We can also see here some more data. This is 2024 as a comparison between 22 to 24. in all 4 regions: Central India, Northwest India, South Peninsula, and East and Northeast India. Everywhere you can see the percentage share of days. So which means that out of 365 in Central India, 73% of days there is extreme weather. So 73%, not 73 days. So it could be heat waves, it could be cold waves, it could be floods, it could be heavy rains, whatever, 80%. So only in South India, we are seeing less than 60%, but we know that they are whatever 46, 52, they are much worse here. The intensity of flooding, the cyclones, everything is much worse. So so the idea to drive behind, it also is visible in this graph. It actually counts the number of days with extreme weather and it compares between 2023 and 2024 in the last 2 years. Almost everywhere except in 1 or 2 states, almost everywhere you can see that the 2024 has got more number of days where there is extreme weather in these states. So the data is showing clearly that the climate is changing, the weather is changing, and we have to think about how whether our models are okay, whether we need to be doing something different with in terms of protecting this infrastructure. So I'll jump right into bridges. So one thing that I want to convey is bridges are lifelines. You all know it. Bridges are lifelines. On the left we can see a photograph of flyover in Chennai earlier this year, just a few weeks or months ago, where you can see that it's heavy raining, and even though the main road is not deeply flooded, the interiors are deeply flooded, and many people are parking their cars on the flyovers, because they want to save their cars, obviously. So and the rest of the things is, road is for carriageways, for emergency operations, movement. So you cannot overestimate the amount of importance bridges carry in these kind of situations. And also on the right side, it is from Taipei, Taiwan. In April 2024, you might be aware that Taiwan had an earthquake, a very large earthquake, more than 7, I think 7.2 or 7.2 magnitude. And in the Taiwan earthquake is an arch bridge, steel arch bridge. I'm not sure what is the bottom tie beam. The top arch is definitely a steel one, and bottom tie beam maybe pre-stressed concrete, maybe steel, I don't know. So you can see it is a 7.0 earthquake, and you can see the bridge. See, I hope you got the point that I'm going to say. It is 7.0 earthquake, and 7.0 earthquake would normally bring disasters, catastrophe to many countries. And Taiwan, along with Japan, is one of those countries which are which is seismically very I would say mature. They have lots of data, they have a lot of experience, their designs are much more advanced and thorough. So you can see in the bridge that the people just don't care. They're just stopping as if they are seeing something on road, and then the bridge moves, and then go on for a 7.0 earthquake. In fact, probably the bridge is there the safest part in the entire region, because in houses, even though the houses are large apartment buildings are seismically designed, earthquake resistant design has been done, you don't know all the facades, all the smaller buildings, light poles, electric street lights, all these things, you don't know their behavior. So something can randomly fly and hit you, and you might die. So you can see that in here the bridge probably is the safest place to be in kinds of earthquake, because it was designed for it. So that's the kind of responsibility that bridge designers have, and not just bridge designers, and the people who are also working in academics to be able to come up with better theories, better models, better data to improve the bridge design codes, and also design philosophies. So I'll jump right into the bridge design. So here I'm showing you a small chart of IRC codes that we use for road bridge design. I did not put intentionally railway bridge design because IRS is still trying to move to limit state, not fully ready, and most of the things that I'm going to talk about are valid for both roads and rail, even though I'm coming from road bridge background and also taking the use of IRC codes to explain. But rail bridges generally have some more stringent criteria. For example, you have all the rails, the steel rails between on the bridges, the tracks that I mean. So the connections between these tracks to the bridges and the tracks themselves. So from operational point of view, there are some more stringent requirements for rail bridges which are not there for road bridges. But these are the general bridge codes that we use: steel bridges IRC 24, and steel concrete composite IRC 22, and concrete road bridges IRC 112. And general design features, it is IRC 5, not IRC 6. It is a typo. IRC 5 is the general design features, and then IRC 6 is for loading specifically. And most of the things that we are going to look at are, I am comparing them with IRC 6. And then there is IRC 78, which only recently moved to limit state method and for foundations and substructure. And then there is IRC SP 114, which is seismic design special publication, and earthquake designs of all bridges in this country are done according to this nowadays. So I'll first go to rainfall and floods. Okay, you can see this image, and I hope you can recognize one thing straight away. This is a photograph from Chennai, and you can see on the right there is a Chennai metro, and on the left there is a bridge. Probably the bridge is constructed some 20, 30, 35 years ago or something. And you can immediately notice that the bridge is already submerged and the metro is not, which means that you realize that there is a difference in HFL, the high flood level, when this bridge was constructed and then now. So it is sad. Now this bridge is probably not anymore safe for operations, and then people are standing just on the footpaths and curbs and even on the crash barriers, in the medians. So okay, so the incidents, you can see that there are 3 different maps: major flood prone states, major cyclone prone states, and unseasonal rainfall prone states. And pretty much all of them, only in some states in south get the heat more, cyclones are in Gujarat on the east coast, and the floods are also there critically, and unseasonal rainfall is in Maharashtra generally doesn't get as much cyclones. And on bridges, what effects do floods and rainfall have on bridges? Is the one that we have seen in the image: submerging of bridges, causing severe transport and relief operation disruption, and then scouring of bed at piers and abutments. Scouring of bed means the washing away of the soil at piers and abutments, and then approach embankment washouts. Approach embankments means just nearby the abutments, while you are approaching the bridge. That is why it's called approach embankments. You can wash out because of the erosion of soil, and then you have a bridge hanging in middle without having any approachability to the bridge. That's what we're talking about. And corrosion of hidden critical elements. So hidden critical elements due to improper deck drainage. So that most of these bridges are steel or steel composite, have some critical steel elements, and sometimes particularly in old days, and even even recently, I would say that the details are not all visible or not all accessible. So there can be water seeping in, and there could be corrosion of hidden critical elements which we cannot see, we cannot figure out, and then suddenly one day they fail. So that these are the effects that floods and rainfalls can bring on bridges. So first thing is that RTL versus HFL. You see that the submerged bridges, and the left one is almost getting submerged. And here we are looking at IRC 5. In IRC 5, there is a discussion about how the high flood level should be decided for a bridge. And you can read, I hope you can see this, that the highest flood levels are obtained from local inquiries from aged persons. Such local inquiries should be made at 3 different locations. Highest level of watermarks left on old structures or erosion marks on banks. So the meaning, of, if you can read even here, the meaning of entire thing is that we are looking at past, which is not entirely correct, because of the data that we have been seeing everywhere. The high flood levels are growing, the discharges are growing, the precipitation is growing. So I do not agree that this is still a valid way to calculate HFL, and then after 30-40 years realize that it was not good enough. And also the clearance, you can see that in the clearance, for depending on the discharge of the rivers, so this clearance is the minimum required clearance as per code between the HFL and the bottom of the bridge. Bottom means the soffit of the bridge. So for 3000 cumex, the large river, the clearance is only 1.5 meters. So I'm not saying to increase it. I'm saying this probably is not enough to enough 30-40 years later when the HFLs change. So is what I mean here. And this is the data that we have, and you can see some of the effects. One is the scouring. The soil gets eroded, under the bridge, around the bridge, and suddenly your bridge has got more length. The pier or the pile or whatever it is has got more effective length, and you all know what happens if the effective length of a compression member increases in the bridge, not just in terms of buckling, but also the lever arm from the four superstructure to the foundation is also quite drastically increasing because of this. So we have design philosophies for all that is not new. And you can see in photos, the left one is, you might have seen in news that in Bareilly, UP recently, somebody just drove off the bridge. The actual story is that there has been an embankment here. The bridge is not fully constructed, I believe. So embankment is there, and that has been washed out. And you can look at the height of embankment. It is, it was supposed to be a spill through abutment, and then embankment was washed out, and then nobody bothered to put a fencing or something, a railing here. And then somebody drove in the night without looking at it. And Google Maps is also not updated, right? That's what we have seen. And on the right side, Seshi sir sent this photograph today. It is from Sikkim, in North Sikkim, and you can see it is a sort of a propped cantilever bridge. You can see it has been built into this abutment, and then there is an additional support, and on this it has been RCC box girder, and probably here it is a simple free bearing which is kept on an abutment, and then there has been a flash flood or some flooding, and then entire ground washed away. There has been landslide, and the bridge is left hanging. So bridge is closed now. You can see temporary bridge erected, and some other works are going on, but still because it is a propped cantilever, even though without propping, it looks stable here at least. So that is one way of being a resilient bridge, in fact, actually. So then scouring of bed and approach washout. There are guidelines available designed for, you have two IRC 89 2019, which is guidelines for design and construction of river trining and control works for road bridges, and then an IRC SP 116 for guidelines for design and install of gabion structures. So when we consider the scout depths, particularly at abutments, we need to be pitching, we need to be doing ripraps, pitching, or aprons shall be provided to be able to prevent these erosions. That is one way of dealing with it. And then I mentioned that there is a issue of corrosion of hidden critical elements. So you can see a couple of photos, and in the left side is a typical ROB. It is not of a particular bridge. It is a typical ROB, road over bridge, and ideas for drawings of many bridges belonging to Indian Railways or NHAI has this kind of structures, and they are closed box sections. They are the top cord, arch, compression cord, and the tension cord at closed box sections welded and of having sizes maybe 800 mm, 1000 mm depths depending upon the spans, and they are galvanized, obviously, but galvanized or painting is being done, or most likely it is painting or aluminum metallizing. These kind of corrosion protection works are done, but the fact is that these are not accessible. You don't know what is going on inside of these boxes, and it's not even like it is leak proof. The splices, the joints, and anywhere water can seep in, they try to be leak proof, but the idea is that there are hidden critical elements in this one joints. And you can see on the right side, it is a bridge in Mumbai outside CSTM railway station, and it was, the story was that there was a collapse in another bridge a couple of years before this incident, where it was found out that the rainwater has been seeping into some of the areas which are getting the steel structures corroded, cross beams in this instance. And then they decided to audit all the bridges, and they audited this bridge as well, and could not detect any problem in this bridge actually, because obviously there is a hidden critical detail, they cannot see it. So this bridge was cleared saying that it is structurally safe, and within months it collapsed. And then after collapsing, people found out that the audit was a failure, and the auditor was arrested, the structural engineer was arrested, and some BMC officials were arrested, but 6 people dead. And the reason is that hidden critical elements and rainwater seeping in through hidden critical elements, right? And so what to do with these cases is prevention through design, no hidden critical elements. And Eurocode, and in particularly in UK, there are no hidden, they are explicitly banned. Nobody approves your drawing if you have hidden critical elements. But in India, it is not the situation. So try to give open accessible steel sections. If you are giving closed sections, the boxes have to be big enough to be able to inspect inside. And then scientific drainage systems, because by drainage systems I meant the size and spacing of the drainage spouts. Hyderabad versus Mumbai, IRC recommends people use the same drain spacing, the drain spout spacing 5 meters or something, and then same drain pipe sizes, and it doesn't make any sense. You all know the amount of rainfall that Mumbai city receives, so it doesn't make any sense. So it has to be the drainage systems are not just good enough in say cities or bridges where the rainfalls are heavy, and there is no maintenance as well. The drains get clogged up all the time, so that not only increases the not only the loading on the bridge, that is not the main concern, but because of the water because of the percolation of the water through these critical areas, it can lead to disasters. So maintenance regime and regular structural audit should be mandatory. So the question I ask here, with respect to the floods and rainfall, is that whether a return period based approach adequate? Because return period means that we say that the heaviest rainfall or the flooding occurs, the frequency, there's a 2% probability of occurring in this year, 2-3%, 10% in 50 years, so on. So, but the climate is changing, the frequency, you've seen the data. So whether that is good enough, and whether our HFLs are good enough is the question. And with that, I'll move to cyclones. And in cyclones, the rainfall part is same as before. All the measures, all the problems are same as before. But one thing that characteristic of cyclone is the extreme wind speed. And wind is generally, for both design purpose and public safety purpose, wind is measured in 2 categories. One is sustained wind and also wind gusts. Sustained wind means, that wind at any point is a continuously changing phenomena. It cannot have a single speed over time. So what people do at these anemometers is that to measure the wind over some period of time and then average it and then report the average wind pressure. So that is a sustained wind. And then wind gusts are the surges of speeds over a short periods. So 3-second gust, 10-second gust, etc. So IRC provides hourly mean wind pressures to design bridges. We'll see in the next slide. So which shall be enhanced with gust factors reckoned for dynamic effects. So here cyclones categories, I'm showing you cyclone categories, and is a 3-minute sustained wind speed in India. So if you go to USA, they give 1 minute sustained wind speed. So unfortunately for designers, we look at meter per second, and it is not a straightforward conversion. So we are not really able to imagine if you see in news that the Visakhapatnam faced 200 km/h wind. We don't know whether our bridge is designed for more than that or less than that, because we don't even know what measure they are giving, whether it is a hourly average wind speed, 10-minute mean, 3-minute mean, etc. So it is important to be able to have an idea of what it is. So here we can see that anything above 61 km/h is called cyclonic storm. If you convert 61 km/h to meter per second, it divides with something like 3, so maybe you'll get something around 20 meters per second. You might think that 20 meters per second is lower, but the thing is here it is 3-minute sustained wind speed. So whereas we are designing for hourly wind speed. So that is the difference. The cyclone, severe cyclone, super cyclone is 221 km/h. So I'll come back to design, how we are designing here. So we are designing with we are designing for 100-year return period, saying that our bridge is 100, service life is 100-year, and then we are using hourly mean wind speeds to calculate the pressures. So hourly mean wind speeds means naturally it is a sustained for 1 hour. So hourly mean wind speed of 33, 34 meter per second generally will be equal to a large storm, cyclonic storm. So that is the case that we are using. But when you see IS 875, the design, the map that is given is not for hourly mean wind speed. It is actually 3-second gust speeds with a 50-year return period. So this is quite severe compared to these numbers, right? So somebody has to make the conversion. So IRC did it themselves. They converted this to a table and then gave us the tables. And obviously, when the first doubt you should get is, yes, we are designing for hourly mean wind speed and we are getting all the pressures, but what if there is short wind surges, short bursts of winds? So for that purpose, these short bursts, we are using something called gust factor in the calculation. So we're directly getting pressure from the code, and then we are using gust factor with, and drag coefficient, everything is depending on the sections, and we are calculating forces. Now, one big caveat here is that highway bridges up to only a span of 150 meters, which are generally not sensitive to dynamic action of wind, is covered in this code. So which means that most of the bridges that we are designing are obviously less than 150 50 meters and in span, and there we directly take the gust factor of 2, which means that we take whatever pressure that is coming with hourly mean wind speed, and then we multiply with 2, and assume that that is enough. So that is enough, that standard. Okay, so far nothing, no problems. The only thing is, what happens if we try to design bridges with spans longer than 150 meters, cable stayed suspension bridges or arch bridges even. So what to do in this kind of cases is, then we come to how wind affects on long span bridges. So the wind, again, it has two parts, as I said, static and also the dynamic, the gust, dynamic behavior of the bridges. Static is the pressure that we're talking about, and even static winds can sometimes cause failure, because obviously, imagine a bridge, imagine a column on which there is a wind load, and if the pressure is more than, or the column is the critical buckling load, that Euler's buckling capacity. So for that of the column or the bridge span members, any of the top chord, compression chords. So if the pressure is causing an ultimate force which is above the buckling capacity of that member, there is going to be an instability, but that is a static part of it. But there is a dynamic part for winds, buffeting and and instabilities. The meaning of that is, buffeting is general behavior in dynamic winds, because whenever there is a gust, obviously it is short term in nature, 2 seconds, 3 seconds. There has to be some disturbance in the response of the bridge. So the disturbance is nothing major. It is like vehicles traveling on a bridge, right? Vehicles don't travel on bridge smoothly. They cause impact, they cause vibrations, this kind of, whenever they hit the expansion joints, whenever they hit some potholes, they create some impacts. So what we do is, we try to convert these vibrations into the from dynamic to static by taking some impact factors, by taking some dynamic factors, amplification factors. So we can do the same with buffeting response also. We can convert this into a static wind pressure just like this with some additional factors. Where we really have problems is the instabilities. So instabilities means, there can be different kinds of oscillations, there can be different kinds of movements, flutters that can happen in a bridge deck whenever there is heavy wind, and wind gusts. So you can see some of them here. Actually, there are 3 of them, and then a graph explaining what these are. The left one is vortex induced oscillation. So you know that whenever there is an airflow passing through a bridge deck or some structure in between, then the air will form eddies, the wind flow will form eddies, which means that there will be short pressures which are pushing the bridge up and down here and there, and that will try to oscillate the bridge. So if the oscillations are large enough, then that is obviously instability. And the second one is aerodynamic issues, which means if the structure is structure is such that it is very slender and it is aerodynamically very badly configured. For example, you see this very too long or too far away kept girders with the deck slab. It is not stable, right? You imagine a long span with this kind of structure. So there is an every chance that the bridge can get twisted and get moved up and down. So that is called galloping or fluttering that can happen, and these are real bad instabilities. You can see in the graph shown here that with increasing wind ratios, how the response is going to be. Vortex induced oscillations, this is what we're talking about, generally happens at a lower wind speed. Normal buffeting response that I talked about, where we just add some factors to the static wind and then design it. And then this is the instability. You can see that the response means amplitude, right? The amplitude just goes up, there is no end, and until the bridge fails, there is a instability at some certain critical speed. So we'll see how this happens. I have got one video for you, which is actually a very famous bridge. Some of you might have already seen the bridge collapse video on YouTube. It happened, it's called Tacoma Narrows Bridge, that it collapsed in 1940 in USA due to a fluttering instability that we're talking about at 68 kmph wind speed. You see that it is not the severe, it is still a bad wind, cyclonic wind, but not the severe cyclones that we see in the east coast of on the Gujarat coast of India. So I'll play this video, and this video is probably 1 or 2 minute long. So just see, and then we'll connect back after that. Oh, there is an advertisement. Okay. Okay, so the bridge cross section is actually a plate girder. So plate girders nowadays, if you see plate girders, you are not. I'm sorry. Okay, yeah, blade girders are not provided for very long spans because of this reason. They are not aerodynamically better performing, and the bridge was fluttering, and the instability was started. And once the flutter instability starts, it is negative aerodynamic damping, which means that negative damping, the air or the wind that is coming in will only make the matters worse, and the amplitude keeps increasing with every swing. So at that time, you can see in the video that they did not know the official terms, no flutter, no instability, no oscillations, because the wind engineering only started after this bridge collapse. Whatever we know of wind engineering, everything started at that point. So they see it as a rhythmic swinging. Okay, and so this is the summary of all these things is that fluttering should be avoided at all costs. So for every cross section of a bridge, by testing, by calculations, you can calculate a flutter critical wind speed, saying that, well, let's say for this particular plate girder, the flutter critical wind speed was only 60 kmph, but as soon as which means that as soon as the actual wind speed crossed 60 kmph, there is a flutter instability. And vortex induced oscillations, they generally happen at lower wind speeds. It can't be avoided, but definitely the amplitudes and accelerations can be controlled to acceptable limits for pedestrian or vehicle movements. and buffeting response is converted into static loading, as I said, and analyzed for ultimate limit state and serviceability limit state, just as we do with the static wind. And wind tunnel testing, because for critical cross sections or for the long span bridges more than 150 meters, it is very difficult and probably even unreliable to be able to calculate whether these instabilities would happen at what pressures and how to convert the buffeting responses to static wind pressures, etc. And so wind tunnel testing is done for calculating the dynamic response of a long span bridges. And the different types of tests, section model test or aeroelastic test can be conducted. Here you can see the picture of a section test, which is trying to find out whether this particular section is safe for fluttering, or vortex induced oscillations at the speeds that the bridge is going to be constructed in. And this is the project that we have done. You can see me on the left with the blue shirt. So this was a wind tunnel lab of RWDI in Thiruvananthapuram, Kerala. So this bridge is located in Delhi. It's a cable stayed bridge, but we are talking about the section, so you don't need to model the whole bridge here. We are only looking at the stability of the section. Okay, and also there are some mitigation measures that are possible. So the question is, what happens if the wind tunnel test or the calculation shows that the flutter response is not good, or the frequency or the amplitude and the frequency of oscillations in the vortex induced oscillations is not good. So there are some aerodynamically suited modifications that can be done. The top one is where we have provided a guide vane, some additional plate which is sort of connected at the bridge at bottom. The idea is that it breaks the wind eddies and the oscillations where the vortexes will not be able to push and pull the bridge so much that the amplitudes are bad. That is one way of doing it. This is also the same project that I was showing in the wind tunnel previously. And the bottom one is quite a famous one. It is Millennium Bridge in London. So you all should try to see the story of Millennium Bridge in London. It opened with a grand ceremony, and then within one day they found out that the vibrations are serious and people are not feeling comfortable to walk. There is a pedestrian bridge, not feeling comfortable to walk. So then they completely reviewed the vibration design of the bridge and then came up with some damping devices. Here there are here there are viscous dampers provided just to control the vibrations. You can see about Millennium Bridge London online. And apart from that, before moving on to earthquakes, there are things about temperature and fire. So in temperatures, the story is same, that in IRC6 gives us some isotherms. Isotherms are the kind of lines where you get the maximum and minimum temperatures for any area. So please, so you design bridges based on this. If you're constructing the bridges in some area, and then what is the maximum, what is the minimum, what gradient it can cause, because most of our bridges are not I would say statically determinate. Some of them are statically indeterminate, so there will be additional stresses that are being generated in the bridges. So all the analysis, but the question remains same. The magnitudes are changing. You can see that there are heat wave prone states, and not just heat waves. We are talking about maximum extremes, minimum extremes. Maximum extremes means that the only issue may be expansion joints not being enough, or there is some local additional bending moments because of the indeterminacy, etc. But the thing is, here on the right you can see the average annual temperature all India from 1901 to 2017, and this black line is an average from 1971 to 2000. You can see that after 2000, none of the year has any data even below or even 1 degree above the average. It has been continuously growing. They have been continuously above average. So probably the data that we have, or the values that we are taking, is not enough. So what happens to bridges in high temperature environment is rising mean temperatures and temperature extremes can accelerate the aging of surface layers. They can lead to cracks, rutting, and therefore there is an increased rate of wear and tear. And also it impacts concrete construction practices, because you might have observed that most of the slabs, most of the foundations nowadays are cast in the nights, not to disturb public. No, that is not the reason. The reason is that placing temperature plays a very important role in construction. So wherever the placing temperature is higher, it will lead to higher temperature during the the formation of CHS gel. So that higher temperature, and eventually when things cool down, the heat of hydration, whatever was generated, the the drop from the heat of hydration to ambient temperature is so high that it will start cracks. That is called earliest thermal cracking. So there are many various reasons or various parameters for earliest thermal cracking, like the shuttering, the mixed design, all these things. But also the placing temperature plays an important role, and also the thermal expansion of the bridges is also heavily governed by temperature. So with respect to the placing temperature, nowadays already in some critical projects, I have done in a couple of projects where we are recommending to use ice flakes in mixed design instead of normal water, just to control the placing temperature. So, and they have to be carefully designed, the mix has to be carefully designed with the ice flakes and the procurement of ice, everything. So probably we'll see that getting more normal, because the placing temperatures are nowhere in our control as the climate gets worse. It is one thing. And also the higher temperatures may lead to an increased risk of deterioration of bridges due to accelerated aging of components, including bearings and joints. And apart from frequent, so how to deal with this is that apart from frequent maintenance, temperature resisting asphalting, because asphalting will lead to cracking and then increased impact loads, everything as I discussed above. And fire design, I will cover briefly what kind of fires that we can expect over bridges. Forest fires, accidental implosion of flammable containers. I think we've seen this just a few days ago in Jaipur, in nearby Jaipur on expressway. And fire accidents in informal settlements. Here you can see that there is some informal settlement, and it is not from India, but you would not be too surprised if something like this is seen in India. So the bridge is built, and you can see the piers and everything, and it has been, the entire area has been used completely differently than envisaged, and there is an every chance that there is a fire accident in this area, and the bridge gets subjected to heavy fire. So when we do fire design, the different ways of doing it. So nowadays it is still a nascent stage. A lot of development is going on. The people are using time domain. Time domain means they are giving something called fire rating. Fire rating is the number of hours, say number of hours after of fire needed for the bridge to convert from safe to unsafe or something like that. So you can see two different materials, how they behave. Is that for steel, assuming that it is a simply supported bridge, obviously the graph will be somewhat different if we consider all the redundancies or the indeterminacies. But the idea is that the stress in the member will remain same because the load is not changing. But as the time is progressing, because of the increasing the time of increasing temperature and the fire, the time spent in the fire, the material yield strength is getting dropped, because obviously the atom structure is getting started to change, and eventually there will be a point where the material strength falls below the stress, and that point is called the fire rating of the bridge, and then the bridge is no more safe. In timber, whereas reverse happens, material strength, it doesn't really matter that much, it won't different. But the thing is, the stress in member will keep increasing because there is a reduction of cross section. The material gets charred, suddenly then the cross section gets reduced, and then the stresses increase, and obviously then again there is a meeting point which is called failure. And this is how the fire ratings are arrived at. And fire design is still in bridges, it is in buildings it is somewhat established as of now. And recently also in UK there is a Greenfell building design report, not design, the fire accident report. A few years ago there was a large scale fire accident in UK which shook the nation completely, and then only recently they have released a thorough complete report of that accident, and it's a very long accident, report. And if somebody is interested in this area of working, they can read that report. So detailed methodologies are still in development, but preliminary, some of the ideas that improve fire ratings, avoid collapse of a bridge, high concrete cover, and intermittent paints, and redundancy in load paths. So redundancy in load paths means if one of the key structural member gives away because of its dropped capacity due to fire, structure should not entirely collapse. There should be some other load path, which means that statical indeterminacy and the different load paths are appreciated, is one way of saying it. And intumescent paints generally applied on steel structures, even concrete. So the thing is, these paints expand drastically when subject to fire, and then they apply a kind of a layer of carbon on the surface. So there is a oxygen cutoff happening. The outside oxygen is not supplied to the structure. So when there is no oxygen supply, the fire will be put off. So that is how this fire resistant coating works. These are also being used extensively for bridges. Okay, now we're moving to earthquakes. So in this, you can see this is an image from Kobe earthquake, Japan. People who have worked in earthquake engineering can directly pick out what the problem is here. And it is just a lack of enough ties, horizontal ties. So there is severe seismic demand, and then all of them got crushed. So what is an earthquake? I'm just give a brief. It is an intense shaking of Earth's surface. The shaking is caused by Earth's outermost layer. And British Geological Survey gives a little bit more detailed explanation. It says that it is a sudden release of strain energy in Earth's crust, resulting in waves of shaking that radiate outwards from earthquake source. So in USGS says that earthquake is ground shaking caused by sudden slip on a fault. So again, here we have another video. It is also a short video, maybe a couple of minutes. What it shows is it is an earthquakes of 20th century. So from 1901 to 2000, it tries to map all the earthquakes on the in the world map, and we'll see how it goes. The speed with which this is getting populated after 1970 doesn't mean that more earthquakes are coming. It just means that we have more data now. So these are called plate boundaries, the tectonic plates, and these wherever there is the plate boundary and the plates intersect, and then so at every plate boundaries there will be the overlapping, the faults, and then the plate, the ridges will be formed. So these plate boundaries are the most common areas where the earthquakes can be expected, and not necessarily doesn't mean that earthquakes happen only at plate boundaries, but most of them happen at plate boundaries. And some earthquakes can also happen within the plates, because there are faults and folds at every, all the geological deformations are there. Okay, so this is the Eurasian plate in where India is there, and you can see that nearby Nepal, and it cuts across Delhi, and wherever these these plate boundaries are there, we have seismic zones 4 or 5. If you see seismic map of India, and within the plates also, because we had Latur earthquake, we had recently also we had some earthquake in Telangana. So within the plates also there are some at faults earthquakes are possible. And this dot for I took this screenshot yesterday from the USGS website. So yesterday there was a mild earthquake in Myanmar, about 4.2 or something. So that was showing the latest one. But otherwise these are the plate boundaries. And so how we are going to design our bridges for earthquakes is that this is the flow that we are going to do. One is how to calculate the magnitude. So you might already all know or the Richter scale, the magnitude that we measure. There are different scales. Richter scale is said to not match very well with the higher earthquakes. So different scales are available. So it is basically the amount of energy, strain energy, or the amount of energy that is released at the source of earthquake, at epicenter, which might be located somewhere deep in the ground, at any location. And then the wave that is created there has to transfer, has to propagate from that point to site where your bridge is being built. And that propagation, and that depends on the kind of ground that we have, whether it is rock or soil or loose soil, whatever, and also the location and the direction of that epicenter. And then once it is propagated to the site, we have local site characteristics, such as the soil, the top top crust soil, and whether there is water table, whether there is chances of if there is sand, for example, the sand can get liquefied. So these kind of actions can happen, and depending on that, there is something called peak ground acceleration that can be calculated every location. So this is the flow to design obtain the ground motions for designing for earthquakes. And then we have this IRC SP114, which gives us the design methodology for earthquakes. So I'll just go through the design philosophy, main design philosophy. So it divides the earthquakes into two different types. One is design basis earthquake, and another one is maximum considered earthquakes. So it is like design based earthquake, return period is 475, maximum considered earthquake, return period is 2500. So one thing you need to remember, if you had forgotten, is that anybody who has shown attention in statistics class would remember that return period of 475 years. That doesn't mean that earthquake happens once in 475 years of that magnitude. No. So it means that there is a chance of earthquake coming every year. The chance of that earthquake is 1 in 475. So if you put this 475 here in T, and in N, if you use the, let's say, the 100 years, which is the design service life of a bridge, then probably will end up that this 475 years return period earthquake, for that, there is a chance that this earthquake comes within the life cycle of that bridge, 100 years. There is a 19% chance. If you do 1 minus 1 by 475 raised to 100, you'll get 19% chance that the bridge is going to get hit by the earthquake. And then if you are designing for larger areas, larger lifespans, MC is suggested to be used. IRC, all the values, all the design methods use this design based earthquake, not the maximum considered earthquake. And on the downward side, on this side, one thing that I want to identify is how we are going to approach this design because our bridges have to be resilient to be able to withstand earthquakes. The approach adopted for design in this guideline relies on the principles of capacity design, where in a strength hierarchy is established. So strength hierarchy, remember that word, we'll discuss that. And in a bridge, to ensure that the damage is controllable, plastic hinges occur only where the designer intends, and the ductile detailing of concrete is covered in this guideline. So it is that the bridge is going to fail, and we are going to control how the bridge is going to fail, and we are going to define what it means. It cannot collapse, it has to keep serving, the rescue operations. That is the target. And strength hierarchy means we exactly know what to fail, what will fail. That is the philosophy behind this earthquake design. And this entire concept of design, the philosophy of design, is called capacity design. So seismic force, you all know that there is a seismic map of India where it is divided into 4 zones. Previously it was 5 zones. One of the zone is now removed. It is 4 zones, 2, 3, 4, 5. And so there is a zone factor here, and the zone factor is zone 5 is 0.36. It means that 0.36 is the peak ground acceleration at zone 5 for the design basis earthquake. Again, it doesn't mean, for the maximum considered earthquake, because we are designing for design based earthquake. Here we are using Z by 2. We're converting that. So this is for maximum considered earthquake. So that doesn't mean that, again, I'm repeating, is that it doesn't mean that in 2500 years, the return period of MCE, 2500 years, this is going to be the maximum ground acceleration, because in I would say Bhuj earthquake, in 2001 Bhuj earthquake, in some of the areas, the peak ground acceleration reported was calculated was 0.6, way above this. The idea is that the probability of this is less. So maximum considered earthquake means in 100 years lifetime or in 50 years lifetime of the bridge, there is only 2% chance that the earthquake is going to be heavier or more intense than this. That is the idea. And we use response spectrum method, where natural time period, depending on the natural time period, depending upon the soil type, we calculate the response of that bridge. So I'm not going into the response spectrum method right now, because that is not the purpose here. And I'll briefly explain what capacity design is for resilience with a small example. Let's say we are going to design one bridge pier, or one bridge, box girder superstructure at 11 meters and then pier of 10 meters high. Now imagine what happens when, imagine that is a fixed pier. So imagine what happens when an earthquake hits this bridge. The first thing that we all need to remember is that earthquake is not a force. Earthquake is a displacement demand, right? What I mean by displacement demand is that the ground just wants to move here and there, right? Ground wants to move. So if your structure is able to keep up, if your structure is moving up, moving around with the ground without any complaints, there is no problem. But the thing is, structure cannot do that, because that there is the mass is concentrated at the top, and suddenly this point is moving away. There is something called inertia. So that inertia is pulling the bridge backwards, whereas the ground is pulling this rightwards. So that is what creating a force. So earthquake is not force. Earthquake is a displacement demand. That is what I would like to repeat. So this is what happens when this ground moves, and then because of inertia, instantaneously at that particular moment, the superstructure tries to stay there, and that causes a pull. So there's a force on this side, and because there is also a dead load, there is also a weight. That weight is now acting far away from the foundation, or the center of gravity of this foundation. There is a second order effect that is created, and then both of these together will create a bending moment. Because it's a cantilever pier, the bending moment is increasing. It is a maximum at the bottom. This is where we are really interested. Now we want this bridge to survive, or we want this bridge to be able to operate even after this earthquake, which means that this bottom section will have to behave in such a way that this demand, the displacement demand, is provided. So how it will behave? We know that there is a it is a cantilever, so there is a bending moment. It is a cross section. You can forget about everything. It is a simple beam cross section. So beam cross section has its own moment capacity, and as you are applying moment on this section, it is going to have some section curvature. So it has got a moment and curvature relation. So for a brittle cross section, without much curvature, the section will fail, because the concrete is going to fail. Whereas for a ductile cross section, the curvature, more curvature is going to be allowed with the same bending moment, which means that we want a ductile cross section which can allow more curvature so that the displacement demand is being met without collapse. That's what we're targeting here. So on the right side, you are seeing, I think you all recognize this is a simple singly reinforced beam cross section, and you have a stress diagram, stress plot diagram, and strain diagram. So we are doing the same thing here. This is the imagine that I am representing this stress diagram. So we have tension on the right side and compression on the left side. So we all know that the way we calculate bending moment capacity for this section is by saying limit the strain, limit the compressive strain of concrete, because if the strain exceeds 0.0035, obviously the concrete is going to crush and then section is going to fail. So all we want here is not let that happen. So we want the concrete to be able to take more strain. We want the section to get more curvature. That is the entire meaning behind the ductility. So we do something called ductile detailing. Ductile detailing mainly is the lateral ties, confining the bridge with the section with lateral ties. Therefore, with that ductile detailing, we have enough evidence. We have experimental evidence that it is possible to allow higher strains in concrete, which means higher curvature. So therefore, the bridge will be able to justify the demand displacement that earthquake is going to place on it. So that's what we're going to do. And that point, because it rotates more than it normally should with help of this ductile detailing, is called plastic hinge, and we are moving in this area where the structure is really ductile and it can take the moments, of course without collapse. That's the end point. So how we do this in practice is that it is called strength hierarchy. Strength hierarchy means at peak seismic demand. Peak seismic demand means the maximum demand. While this plastic hinge undergoes high strain, the high strain is the more curvature. No other section or element should fail. That's the main philosophy behind this entire thing. No other section or element should fail, which means that the foundations, what are all the other sections in this image? The foundations on the pier sections outside the plastic hinge, because the plastic hinge is only at the bottom location. So pier sections outside the plastic hinge, the foundations, all should be designed for capacity design rather than the actual bending moment. So what I'll just give a brief explanation of what it is. Imagine this is a simple pier that we showed previously, and now there is some force due to earthquake that is called design bending moment. The bending moment diagram is like this, and at the bottom you have a ME. Now you design a cross section for this. You provide reinforcement, you calculate the moment of capacity moment, and then the cross section has some capacity which is called MRD. Obviously capacity will be more than ME, because otherwise it will fail straight away. So MRD is the capacity of the cross section. So you all remember that the capacity of cross section, for a simply supported beam, 0.138 FCK BD square, it has got its own factors. FCK, the 0.138 is coming for, you take only 0.446 per, FCK, right? Which means that concrete strength is taken only half of it, which is available. The same with the steel. So the problem is that ME is, this MRD is not true. This MRD is vastly underestimated. The real strength of the section is much higher. So let that be MO. It is called over strength capacity, which means that plastic hinge area, which means that this section will not fail unless the moment reaches MO, not MRD, because this is the factor of safety that we have. So the idea is that unless the plastic hinge fails, no other section should fail. The foundation should not fail. The section here should not fail. So we should design everything else based on the real capacity, not the factored, lowered capacity. So MO is the over strength capacity. We directly design the foundation with MO. You're getting what I mean, right? So the foundation, the strength has a capacity, section has a capacity of MRD. The true capacity without all the stripping of all the factors is MO, which is over strength capacity. We design foundation with it. Now we draw a line here. This is the bending moment capacity of the, not the capacity. If we draw a line here, then which means that it can take the amount of load F, if the F is applied here, the F which can convert, which can give MO here. That's for the amount of low force it can take. So that is the over strength capacity. Now we have MRD. So this MRD, it is called the length of plastic hinge. The length of plastic hinge will depend upon the size of the section, the slope, etc. So this is the point. And if we just plot this one, you have a magenta color line called MC, which means that the strength of plastic hinge is this zone. and there you can allow lower strength. So for example, if you take a mid section, let's say a section at this point, actual bending moment from the loads is only this part, only half of ME or whatever. But if this section can take only this area, it will fail before the bottom part fails. But we do not want this middle section to fail because it cannot rotate as much as we want. We want only the bottom section to reach that level. So everything else should be having capacity to suit that. That is what is the meaning of capacity movement. Let's say we want to we want to curtail the reinforcement. How will you do? Is that we have to curtail reinforcement at a level where after the curtailment the capacity should not go beyond this one. So this is the meaning of the capacity movement, where we are saying that other than the plastic thing, no other section is going to fail, or when the earthquake comes, and therefore we are having a ductile structure. So shear force should be based on, again, this MO. Shear force should not be F. Shear force should be MO divided by length, because shear failure is brittle. So we have to design with overstrength factor. And this is a brief of confining reinforcement in IRC. This is how confining reinforcement is showed with all the ties. There are calculations depending upon the size, and they are really heavy. In the first image that I showed to you of Kobe earthquake, that there was just not enough confining reinforcement. And one more thing for a resilient bridges is the dislodgement prevention. You can see that at every girder there is a seismic arresters or seismic blocks extra, which are coming out and which are trying to hold. They are just to ensure that even in case of worst earthquake, failure only happens at the bottom, and there is no chance that the superstructure will be dislodged and the bridge becomes a failure immediately. And there are other ways to deal with bridge earthquakes. That is, one is base isolation. Base isolation is to kind of provide a very flexible material instead of instead of fixed bearings. So you're creating a spring in series. So you have one spring of the stiffness of the pier and another spring here. So these two together reduce the seismic response. So how it reduces seismic response is by two ways. One, the time period increases. Why the time period increases? The time period is directly related to the length and the stiffness. So the stiffness is getting reduced because of springs in series. The time period increases, which reduces the SAYG. And the other way is damping. All these materials have inherent damping strength. So other way is damping. Another way to use is external damping. We use fluid viscous dampers. We use tune mass damper. This is the tune mass damper is of a building, but fluid viscous dampers are more popular in bridges. What these two things do is just an explanation here. You see, this is the response, elastic response spectrum graph. So whenever you give base isolation, because the time period increases, so you are moving from this point to this point, the right point. So as soon as you are moving towards the right, because of increased time period on x-axis, the SABG reduces. So suddenly the seismic response is reduced. That is how base isolation works. Whereas damping, you all know that all the seismic response spectrum graphs that you have in code are for 5% structural damping. Whereas when you are giving more damping by the way of lead rubber damper or high damping elastomers, so the way to do is you increase the damping percentage. As you increase damping percentage, you get to shift these graphs below, and you get better SABG values. Therefore, the seismic forces are less. And the one way to the maintain comes part of a maintenance is that structural health monitoring. Structural health monitoring is a non-destructive in situ structural sensing and evaluation method. Uses a variety of sensors. You can see the number of sensors for a typical bridge: accelerometer, strain gauges, wind speeds, displacement gauges, corrosion gauges even. So all these together equipment will give a sense of the bridge performance in its real time while the bridge is in functioning. This is one of the bridges, currently the world record holder for the longest span, 2023 meters from this pier, this pylon to this pylon in Turkey. And this is the structural health monitoring system. And this is called control room. I've been to this bridge, and this is the photograph I took, the control room photograph. So here the extensive monitoring is going on for this bridge, and that is how the bridges get resilient. There, what is going to happen whenever some earthquake, some natural hazard is going to come, and the response can be immediate. And the last few slides is that multi-hazard scenario. So now, as I told, that the frequency of each hazard independently is increasing. So we have a situation where there can be not only one hazard, there will be number of hazards can be done, and statistics-based research is underway to deal with this problem. For example, you see this in in the world hazard map given by Munich Re is that different types of hazards are categorized: geophysical events, meteorological events, hydrological events, climatological events, and all of these things are happening. And if you see, particularly in India, it is a combination of everything in some cases. So it is important that hazard multi hazards are considered, not just one hazard, because your bridge has to keep functioning. And in National Building Code 2016 there is a multi hazard map of India. Honestly, I just cannot figure out, it is kind of a brain teaser. For example, if you say this is Bangalore, what zone it is, I don't know, because I see so many different zones for the same color. So anyway, this needs more explanation and improvement, but the idea is that it tries to classify areas where multiple hazards are going to come, and for example here wind and cyclone, wind and earthquake, etc. So you need to be designing for these things. How to decide? For example, you see in the right side is that it is a bridge which are already there is some scoring happened. So because of scoring, suddenly you have higher column lengths, right? So higher column lengths, foundation is exposed. So the earthquake forces or the earthquake behavior, even the capacity of the column cannot be same as before. So you have to kind of take them together, that one hazard happened and then the bridge is going to change and then there is another hazard happening. So some things are being done already in code. For example, IRC says that you have to consider a scoured length for the seismic design by reducing scour by 10%, but still it is deterministic. It is not scientific, it is arbitrary. So data driven probability models are still under development. There are a lot of work to be done in this area as well. So I conclude here by saying that resilient bridges are those with serious risk eliminated by design itself and then performance monitored throughout their life, and an effective maintenance regime is in place. And return period based approach may be not adequate in changing climate. Some things are going on here already in finance and everywhere this is there, that the mean and standard deviation are not stationary. We cannot say that there is a characteristic value. Even the means are non-stationary, standard deviations are non-stationary. There's a better probabilistic models are being developed. And then design of all elements should be based on that hierarchy that I said before, that on a philosophy that keeps the bridges in reasonable service even during and after disasters. So I conclude there. Thank you.
Thank you very much, Jithendra sir. You have given a beautiful session with the deep insights.
I'm done. Thank you. Any questions? Anything?
Can you hear me, sir?
Yeah. It's already 7:35. We'll take the questions later. Anything? Yeah. So Jithendra,
Sir, you
it's
are on
like
mute, I guess.
thank
We
you.
can't hear
Thank
you.
you so much.
We can't hear you.
Yeah, I think just 1 minute.
Yeah, you are audible, sir. Sridhar sir, you are audible.
Yeah, I'm audible.
Yes, sir.
Yeah, Jithendra. Yeah, thank you. Within this 1.5 hour, you covered all the things,
I
right
can't hear
from
you.
all the. Hello.
Raghu, can you hear, sir?
Yeah, am I audible?
Yes, sir. Yes, sir.
Yeah,
Jithendra sir,
I'm audible.
Yes, sir. Yes, sir. Yes, sir. All is fine.
Yeah, now it's okay,
I
Jithendra.
can't hear you as well. I'm not sure the problem is with me or.
Yeah, you are audible, Jithendra sir.
Yeah, we are hearing you, but I don't know why my voice is not coming to you. Hello,
Sir,
Raghu?
you can carry on, sir. You are audible, sir. No issue, sir. Actually, there is a problem from Jithendra sir, I think.
Yeah. Huh? So I think
Can anybody else
my
hear
dear
me other than Raghu?
Yogi,
It is audible, sir.
are you able to hear Jitendra sir voice?
I'm able to hear everyone, like
Yeah.
Shishidhar and Raghu Babu.
Sreenivasulu sir,
Okay.
welcome to this session, sir. We will wind up this session.
Yeah, welcome, sir.
No
Welcome.
worries, no worries.
Yeah, Jitendra, anyhow. Yeah. Thank you, my dear participants. We are closing this session. Jitendra has given good presentation covering all the topics pertaining to bridge engineering. Anything related, please contact him separately. We'll share you. Now we'll start the second session of today's meeting. So once again, good evening to all of you. It's an honor to welcome our next speaker, Mr. Srinivas Garu, to ATAL FDP. Today, we are privileged to hear from Srinivas Garu, whose expertise helps to gain invaluable insights on offshore structures and some insights on fatigue and earthquake-related concepts as well, technically. Sir, he has worked as a senior engineer from 1998 to 2001 in L&T Valdale, a deputy lead structural engineer for Quarter Petroleum's 2001 to 2005, and he worked for Technip Senior Structural Engineering 2005 to 2007, and PMC Structural Engineering 2015 to 2016. McDermott International Private Limited Singapore Senior Structuring from 2007 to 2011. He was a principal structural engineer 2011 to 2014 and in the engineer manager 2019 to present. So by seeing his profile, we can say that he worked in all the reputed engineering firms. We are privileged to have you here, sir. So thank you very much for sparing. I came to know that you are busy, but even then you are dedicated your time to us. Thank you very much for disturbing you on this holiday session. So once again, I welcome you. Please, now the mic is handing over to you, sir. Please go on, sir. Thank you very much, Srinivas Garu, once again.
Thank you, sir. Thanks, everyone. And first of all, I would like to congratulate, thank you, JIthendra. Excellent presentation. I thought of joining just at around 7:20, but if I would have joined at late, then I would have missed a great presentation. Thank you, JIthendra. It's really very interesting. Okay. So coming back to my presentation, it's actually I thought of presenting on the fatigue, but because of the time, I'm on holidays actually, so I could not spend much time. So then I discussed with Dr. Raghu Babu, and then concluded that we will present on the offshore structures, overall structure, offshore structures. So I'm Sreenivasulu. Currently I'm working as a senior manager in subsea engineering, but I'm presenting on the offshore structures. Subsea engineering and offshore structures both are different. Subsea engineering is now I dealt with the structures which are in ultra deep and ultra deep waters, which is around more than 1,000 meters of water depth in waters. Yeah, let me present my presentation. Please let me know if you have seen my screen.
Yes, sir.
Thank you, Mr.
Yes, sir. We are able to see.
Yeah, this is about the offshore platform design today I'm going to present. Okay. So offshore platforms is we have in India plenty in Mumbai Highway and in our KGD basin also, Krishna Godavari basin, and some in Gujarat also. So the main operators, oil operators in offshore field. Actually, oil extraction happens on one is onshore, that one is offshore. I am more into the 100% into the offshore oil extraction business. My company is EPCIC contractor, engineering, procurement, construction, installation, and commissioning. So we do entire thing and then we hand over to the customers. Our customers in India is ONGC and Reliance. Okay. So mostly, yeah, we are doing outside India projects only. So overview of these platforms. These are mainly platforms are used for exploration of oil and gas from under seabed, and it will be processed. So the first offshore platform was built in 1947 in coast of Louisiana in USA in the just water depth of 6 meters. But today there are over 10,000 offshore platforms around the world. So platform size depends on the facilities. If it is going to be a topsides is going to have just an wellhead platform or a process platform, or it is a living quarters or utilities platform. Wellhead platform means just it will have a Christmas trees and it will drill under the seabed and just extract the crude oil and then send to the nearest process platforms for processing. That is called wellhead platform. And process platform is it will receive the crude oil from various platforms like wellhead platforms and subsea facilities, and it will process the crude oil and then it will transfer to the onshore refineries. There it will go for the further treatment, like it will be divided into so many other products. Okay, so crude oil is not just only the I mean, like a petrol or diesel. It will be there will be so many byproducts. So those things will happen in the refineries, like we have one in Jamnagar, Reliance refineries, like that. We have many in Baroda also. We have IPCLs. And then we have a living quarter platforms. Living quarter platform is purely meant for only for the people, and who will be supporting the process platforms. Okay, and also there will be living quarters will also have sometimes workshops, and then there will be some utility platforms. Utility platforms means which will be used mainly for to inject the water into the reservoirs to increase the pressure, or gas, those kind of the utility platforms. So these platforms, the classification of water depth in offshore, it is a 3 types. It is a shallow waters, deep water, and ultra deep. Shallow waters means up to 350 meters of water depth is called shallow waters, and anything up to 1500, between 350 to 1500 is called deep water, and more than 1500 it is ultra deep water. The basis is based on the US Mineral Management Services. This water depth classification has been done. So typically offshore platforms, we can see in this presentation, in this slide, can be broadly categorized into 2 types. One is the fixed platforms, other fixed structures. Fixed structures you can see in the first 2, which are fixed platform FP and the compliant tower. These fixed platforms, and we can have one more. This is the steel structures. We can also have a concrete gravity structures. And the second one, the compliant tower, which will be used only for the greater water depths, like a 300 meters, something like that. So where we will use the fixed platforms. So I'll go back to the previous slide. Fixed platforms, usually we use up to maximum of 175 to 200 meters is a maximum water depth. Okay, so anything ranging from 6 meters and up to 200 meters, it is viable and feasible to install, and feasible to install the structures. If it is over 200 meters, it is commercial, I mean, financially it is not viable also. So we will go with that time we will go with the different options. Like this thing, compliant tower, is also a steel structure, but it will be 300 meters. It will be built into the pieces with the swaged connections, one frame over the other. It will be with the swage connection, it will be built. The compliant tower will have will attract a lot of lateral deflections. So wherever there is no such issues with the lateral displacements, there we will go with the compliant towers. Compliant towers will not have any living quarters, because if people are there on the top, then with this kind of deflections, it is an issue with respect to human factor engineering. So usually compliant towers is unmanned platforms, whereas fixed platforms is a manned or unmanned, both. And the next one is tension leg platforms, mini tension leg platforms, which I will go here, and floating production and subsea systems, SPAR. SPAR is a one system. Another one is a FPS, floating production systems, and then FPSOs. So these tension leg platforms is basically, I'll go back to previous slide. Tension leg platforms usually will have a platoons. You can see the platoons here. Basically the platoons, the buoyancy, whatever we will get here, will be much more than the top side's weight, so that it will always tries to float only. And then we will have with the steel ropes, okay, steel ropes, and with the attached to the ropes will be attached to the piles underneath on the seabed. So the ropes will always be on the tension. That is why it is called tension leg platforms. So that also will have a kind of lateral displacements, but not huge. SPAR is also similar to that. It is also a kind of tension leg platform. The diameter of that spar itself will be very high, and that will create a lot of buoyancy, and then it will be tension guys will be provided to the seabed, which will be anchored to the piles. So that is a philosophy for the spars. And for the floating production systems and FPSOs is also the same. So basically all these tension leg platforms will be used where the water depth is very high, like if it is exceeding 250 meters to 300 meters, it will go with the tension leg platforms. So jacket platforms, these jacket platforms are space steel structures, space frame structures with all the tubular members supported on piled foundation. Again, pile is also a steel tubular. Okay, and usually the diameter of the pile ranges from 60 inches to up to 108 inches also. Again, it depends, the pile size depends on the top side's weight and also the soil characteristics. And these fixed platforms will go for a moderate water depths up to 200 meters, because after 200 meters it is not possible to install as a single piece. That is the reason we will go up to 200 meters, and it will be commercially not feasible for if it is more than 200 meters. Typical offshore structures will have a these top sides will have a, I call it as a top sides on the top, whatever you see on the red, it will have a main deck and a mezzanine deck and cellar deck, and a heli deck also will be there. So the deck structure is supported by deck legs. The deck legs is it will be put on top of the piles. So the piles extends from above the mean low water through the seabed into the soil. The piles will, there are two types of piles. One is piles through the legs of the jacket, and another one is a scut piles. If the water depth is 300 meters, then we no need to put piles through the main legs, because we will have to spend a lot of steel for that. So instead, that what we will do is we will have a scut piles at the near the seabed. We will have a, say, 10 meters to 15 meters. We'll have a separate separate sleeves, and then over the sleeves, then we will drive the piles, and then we will grout it. So that's how it is for the deeper two types of pile foundations: scut sleeves and piles through the main legs, jacket legs. So we can see here, these are the piles through the sleeves. So where the water depth is more, then we have a cluster of piles here, and then piles will be driven through this. So underwater, the I think I covered this one. The natural period of these fixed platforms is one thing which we usually limit to 2.5 seconds, and it is subjected to the, of course, it depends again based on the mass and the height and all those things, and also with the wave period, sea state also. To avoid the amplification due to the wave loads, we will just keep it up to 2.5 seconds, because majority of the times all these platforms are manned platforms. So anything more than 2.5 seconds is an uncomfortable situation for the persons working over there. 95% of the offshore platforms around the world are jacket supported only. So this is the compliant tower. It's a narrow, flexible framed structure, and again it is also supported with the piled foundation, but piled is again sleeves. You can see the sleeves here in the bottom near the seabed, and has no oil storage capacity in this. Whereas in other tension leg in fixed platforms, sometimes we used to store the oil in the jacket legs itself. When the piles are in the scut sleeves, then we can use the jacket legs as a storage for the chemicals and oil also. Not the crude oil, but for the day-to-day operations for the platform, we use that as a storage capacity. The production in these tension leg platforms is through the rigid risers, and all this, and also any services will be through the flexible catenary steel pipe. That is basically umbilicals. These kind of structures will undergo a large lateral deflections because of the wave loading, and it will be used for moderate water depths of 600 meters. But nowadays nobody is going for this kind of structures for many regions, because 600 meters they go usually for nowadays FPSOs or tension leg platforms, this kind of the things. Natural period is kept above wave period to avoid amplification of wave loads for these compliant towers. And this is a concrete gravity structures. This is the olden days. We still have some concrete gravity structures around the world, not in India. Concrete gravity structures are it is just based on the gravity only. They will be built in the dry dock, and then from there they will once it is flooded, then it will float. Then the way they tow it to the site locations. This is a very old technology. We still have this kind of platforms working in, especially in Australia. But nowadays it is completely, there is no concrete gravity structures because they could see the lot of deformations over the period of time. So what happens with this deformations is when the pipeline and connecting the risers, it will induce a lot of stresses when the platform settles too much. Okay, so that is the reason that they are not going for the concrete gravity structures. So if you go with the fixed platforms, it is a fixed, and whatever the deflections over the 100-year also we will estimate, and that settlements we will induce in the riser design. So there is no issues in the riser design, but this is not that that kind of feasibility is not there in this gravity based structures. The only advantage here with this is less maintenance because of the corrosion and all those things. This is the tension leg platforms. Tension leg platforms are floating facilities that are tied down to the seabed by vertical steel tubes called tethers. The characteristics makes the structure very rigid in the vertical direction and very flexible in the lateral direction. The vertical rigidity helps to tie in wells for production, and the horizontal compliance makes the platform insensitive to the primary effect of waves. And it will have a large columns and the pontoons and a fairly deep draft. Otherwise, to have the buoyancy. TLP has excess buoyancy, which keeps tethers always in tension. Topside facilities, a number of risers, etc. All these things will have to be fixed at pre-design stage, because I mean, like a future expansion, we cannot have in this kind of the things, because buoyancy has to be fixed in the beginning itself. We cannot have extra buoyancy also for future, because in that case, then it doesn't work for the current demand. So we will have to have everything finalized design in hand, all considering the future and everything to be installed at the one place. Then only this kind of the platforms are suitable. These are mainly used for water depths more than 1200 meters. And it has no integral storage, but all these pontoons, you can see these pontoons here. All this it is not just buoyant, but inside this there will be a lot of workshops, utilities, and offices. All these things will be there. It is a very sensitive to topside load and draft variations as tether tensions are affected. The semi-submerged platform is also similar to the tension leg platforms, only that due to small water plane area, they are weight sensitive. Flood warning systems are required to be in place for this. And topside facilities, number of risers, etc., have to be fixed at pre-design stage itself, like similar to the tension leg platforms. And it will also be used for ultra deep waters, I mean more than 3 kilometers water depth. These things are also will be held in place by anchors connected to a catenary mooring system. We can see that catenary mooring system here. All these things. This is semi-sub platform, but this is in the dry dock. What you can see, it is not yet launched. This is a spar which we have discussed before. The concept of large diameter single vertical cylinder supporting deck. The first platform is in US in Neptune, by Neptune. It is in 1997. Neptune is an operator. 1997, the first one. But nowadays, nobody is going with the spar kind of platforms. Spar platforms have a taut catenary moorings and deep draft. So the natural period is about 30 seconds because it is just a circular and a deep this thing. So it will have a high natural period, and it will also be used for ultra deep waters. The center of buoyancy is considerably above the center of gravity, so making the spar quite stable. So due to the space restrictions in the core, number of diameters has to be predetermined. So the core means the spar itself, the diameter is fixed. So we have to fix everything, number of risers and all those things. Okay, risers means, I'm using this word many times. Risers means it will be either inflow or outflow of the fluid. Okay, either we are collecting it from the nearby small wellhead platforms and sending it here for a processing, or after processing we are sending it back to the onshore refinery units. These are all called risers. Ship-shaped vessels, these are FPSOs. These are quite popular nowadays. Any deep waters nowadays, to be frankly, we are having only two types. One is a fixed type, fixed offshore platforms. Another one is a ship-shaped vessels, FPSOs. We have in our KG Basin also. I recently involved in one of the project, KGD ONGC's project, and then a Reliance project also, where they have FPSOs. These FPSOs in ONGC, they have used even at the around 650 meters water depth also. So these FPSOs will be stationed at there, and then all the risers will be connected there. So it will connect there, and then it will process. Either it can stay there and or it can move also. Once the basically these FPSOs are suitable for marginal fields where the reservoir capacity is less. So it will collect over the, suppose let's say 5 years after the reservoirs are no more reserves are there in the reservoirs, then it can move to the next site, and then we can use there. So that is advantage with this ship-shaped vessels. So the top sites, usually any offshore platform top sites will have a facilities with all these equipments. Like first thing is a drilling rig. Drilling rig itself will be there, so which will be used either not for drilling itself. Drilling will be happen before itself. Sometimes even after the installation of the platform also. But for maintenance purpose, drilling rig is required. So drilling rig mast will come and sit on top of the platform, and compressors for injecting the gas, compression gas or water injections also, because gas and water injections are whenever the pressure drops in the reservoirs, then we will inject the water, and then the gas or oil will come onto the platforms through risers. And then gas turbine generators, and then lot of piping, HVAC, instrumentation, all these things will be there. And also accommodation for operating personnel and cranes for equipment handlings, and for personal movements, helipads and boat landings, this kind of the stuff will be there. That is for the top sites. So platform installation. So how the jackets and these things will be installed is typically it's an entire platform will be installed in two types. Jackets will be in, let me go to the other presentation where I think I can present it better. Yeah, here I can show this one. Here, hope everybody is able to see my presentation. This one, right? Thank you.
Yes, sir.
Thank you.
Yes,
This is
sir.
the jacket. This is the jacket structure. Underneath this is the sea level, and this is the jacket, and above that one is a deck, and this is the sea floor, and these are the conductors. Conductors is which will be driven to the oil and gas reserves. Usually these well conductors will start with a 20-inch on the top. Then by the time it reaches to the reservoir, it will be like a 2-inch pipe only. So with just 2-inch pipe is sufficient enough if that from the reservoir to collect with such a huge pressure. Okay. So usually these conductors will be driven almost 2 kilometers also from the seabed. So these are the piles inside the jacket leg. You can see this will go based on the capacities, maybe around 60 meters, sometimes 100 meters up to that depth. This is a fixed offshore platform. You can see here. And these are the various analysis which we do for the jacket and top sides. For jackets, we will do the loadout analysis. Loadout analysis means once we fabricate on the fabrication yard, near to the jetty side, then from jetty, and it has to be transported onto the transportation barge. Okay, transportation barge. So how it will be loaded out, that is the one loadout analysis. Then once it is transported onto the barge, then it will be transported to the site, offshore site, which may be a few kilometers, or it may take 3 days or 30 days, it depends. Okay, so that is the transportation analysis. So transportation analysis, we will design the structures for the motion accelerations, and then once it reached to the site, The jackets will be installed either by lift or by launch also. And then next sequence is, once it is lift or launch, then we have to append the entire structure, because it will be in horizontal mode. Then it will be appended, and then it will be lowered down to the seabed. And then once it is on the seabed, it is not having any piles, so we have to check the jacket structure stability for the on bottom stability. Without piles, at that time we will just have a mud mats, so we will have to check for the 1 year 1 year environmental conditions for the on bottom stability. Then once the platform is installed, put on the seabed, then we will have to drive the piles. Piles will be not in one segment, it will have a different 3-4 segments typically. So based on the on bottom stability, each and every corner they will be putting one segment, and then second segment, like that, lowering down and then driven through the hammers. So once that is done, then the platform is installed. After that, there will be in-place analysis. In-place analysis means in-service conditions, when it is during operational conditions. Operational conditions, we will design it for two scenarios. One is a normal operating scenario. Another one is extreme storm conditions, like 1,000 years, 100 years in India, we as per the ONGC guidelines and all. But usually in many other countries, we design it for 1,000 year storm conditions. And seismic analysis. Seismic also we do for it. Seismic analysis, we will do it for wherever it is identified. And then fatigue analysis. Fatigue analysis also, because most of the joints are tubular to tubular joints, and joint is an important thing. And because of the wave, because of the currents, lot of reversal of stresses. Because of that, the joints will be very sensitive. So we'll perform the fatigue analysis. And then the vessel impact analysis, because the surrounding platform, any vessels will come and hit the jacket structure. So there is a possibility that, so we will do the vessel impact analysis, considering the mass of the vessel and approach speed and all these things. And then there will be so many miscellaneous designs, like vortex induced vibrations, and then these are all minor miscellaneous designs. So they will not govern the platform, the failure of these miscellaneous designs will not happen platform to collapse or something like that. So besides that, the platforms will also be designed for this CP, cathodic protection. So what we will design mainly is member check, and then joint punching check, and then pile capacities and the deflections. That is about the jacket design. When it comes to the top sides, also the same. Loadout analysis same as a jacket. Transportation similar to that. And the top sides installation, when it comes to the top sides, either it will be installed by lift or float over. Whereas in jacket, if it is a heavy, then we do the launch there. But for top sides, it is a float over analysis. And then the in-place analysis is same as jackets, and seismic analysis, fatigue analysis, and other miscellaneous designs. Miscellaneous designs include in top sides many, like we will be having a many rotating equipments. So the foundation of the rotating equipments and the piping supports, all these kind of the things, material handling systems, and then vortex induced vibrations, all these things will be there. Majorly we use the API codes, American Petroleum Institute, ISO, International Standards of Organization, and then DNV, DETNAT, Veritas, NARSOC, and Nobel Denton guidelines. Actually, now DNV and Nobel Denton is one. It is a one organization now. Here I can show some pictures where you can see the loadout analysis. Loadout analysis can be done. Loadout can be done by the 3 ways. One is by skidding. Skidding means just from the it will be skidded, pulled from the cargo vessel. It will be just by skidding only. So in that case, we will have a racking and displacement loads. Racking means, so the first breakout load. First time, because the jacket, this structure, to build the structure and the yard itself, it will take a minimum 1.5 years. So during the 1.5 years, it will be settled enough. So first time when we wanted to move the structure, it will have a braking force will be much higher. Once it moves, then it will be less. So that's why the braking load. Then the racking loads, when we try to pull that one, racking will be like it won't be equal loads on either side. Sometimes it will be 40% this side and 60% another side, something like that. So for that consideration. And another one is displacement loads. Once it crosses the jetty, that means the quay side, and then before going onto the barge, so it will have a displacements, because the barge will have a ups and downs because of this drafts. Okay, so because those displacements also we will consider and design that condition. And the second one is trailers. You can see that here we can have a SPMT trailers here. So these trailers will also be used sometimes. So the advantage with this trailers is we can engage these trailers after the fabrication is completed, then it will lift. And while traveling on the yard, if it, from at one end of the yard to the quay side, even if the ground is not smooth, if it is having some undulations, the trailers will automatically adjust the self-propelled this is. So automatically either low or up, it will automatically adjust, so that it will not induce any stresses into the structure. So that is advantage with the trailers. And sometimes if the weight is less, and then the cranes in the yard itself will be used for the lifting. So you can see it here with the two cranes, they are lifting it, and before placing it onto the cargo barge. This is about the jacket loadout operation. And I will come back to the my previous other presentation about the loads and designs and all later, after going through this one. Then this is the jacket sea transportation. It will be transported in two ways, either in horizontal mode or in vertical mode. It depends on how you are installing it. Okay, so during this time we will have to design the structure for the inertial loads due to the transportation vessel motions, basically roll, pitch, yaw, and sway, surge, and heave, linear accelerations, linear and angular accelerations. And the design input is for this, whatever the this input will be, I mean the total reactions, we will use it for sea fastening designs, and also the barge checks also, and also ensure that our structural members are capable to withstand all the inertial loads. Then this is one of the method for a jacket installation. So this is a jacket, we are installing it here. It is by lifting. So here it is a total weight is under the dynamic loads will be considered, and skew loads also will be considered, because the slings will not be having equal length at the center of gravity of the structure. It will have some variation in length. So because of that, we will have a skew loads and some COG variations also, because whatever we consider the weights and all those things is based on our most of the times we won't be weighing it, especially for the jackets. In such cases, we will use the COG variations. We will consider some envelope based on the DNV guidelines or client envelopes. We'll consider them in the design and verify them as usually member stresses and giant punching checks and all these things. Based on the output of this is we will select the slings and shackles. Okay, this will be used up to maximum we can lift 4,000 tons, and now we have a one crane is there in the entire world by Allseas, which can lift around 5,000 tons also. Anything more than 5,000 tons shall be installed by a different way. So this is a different way, means launching. If the jacket is too big and is too heavy, like one of the project where I'm currently doing for Vietnam, which is a 9,500 tons jacket, so which we cannot lift by derrick barges. So we have to have a installed by launching only. So why all these jacket structures will be in will have a only tubular sections. So this is the reason we will have a tubular sections. It will create a lot of buoyancy. So because of that buoyancy, we will generate the buoyancy. It will generate the buoyancy. If that is not adequate, then we will provide the additional buoyancy tanks also in this, which will be removed after the installation. So because of this buoyancy, the jacket will, even after, you can see here, this is the first position, then the installation barge itself will be trimmed in the sense ballasted. Ballasted means here this corner they will put more water, or they will take more they will take out the water here, so this will tilt. So it will go up to 2.5 degrees maximum, or up to 3 degrees, then it will slide. Then we will have a tip over there. Over the tip it will go, and then it will slide into the sea, and then it will float in this position only. So we will design all these things: buoyancy calculations, reserve buoyancies, and we'll also consider sensitivity cases like any damages buoyancy damages, like you can see here the skirt sleeves where it will have a diaphragm closures here, so we will consider the buoyancy effect of these things also. If suppose in case if the diaphragm closures fail, we will ensure that it will still float. So once the jacket is float, then it will be appended. So that will be the next one. So once the jacket is, you see that here, so once the jacket is in this position, then we will append it and then lower down onto the seabed. How we can lower it down is we have to do a controlled flooding. Then we have to open it here and then flooding. Then only it can go down. Otherwise, it is a buoyant. Then it cannot go on its own. So we have to flood with the. We have to cut the top. Divers, welders will go there and cut the top portion, and then they will flood the water, and then it will be settled on the seabed at the desired location. So this is a piling sequence. You can see here in this. This is a skirt sleeves. So here you can see that pile segments, and there will be on the top, there will be a guide, and from there they will be driving with the hammers, and then last segments will be underwater hammer. So okay, within the underwater hammers also will be used for this kind of the things. But for if the piles are within the jacket main legs, only the above water plane only the hammers is required. So this is you can see here, this is a hammer, and first when we place that first P1 segment, it will have a self penetration. So once the self penetration is happened, then we will hold it with the brackets over here. Then the additional next segment will be welded. Then the next segment will be released. Then it will go after the self penetration. Then it will stop. Once it is stopped, then we will place the hammer. By placing the hammer itself, again further it will go some more, because the hammer itself will have around 150 tons to 200 tons weight. So it will have a further. Then after that, once it settles, then we will use a number of blows for each pile segment. All these things will be performed in the pile drivability analysis. We will calculate how many blows is required for each pile segment, and we will also ensure that none of the segments is going to stop in the sand layer, because once it settles in the sand layer, then next layer it is a very difficult, it is almost impossible to drive. So either we will place in the clay, either in the above, or we will make sure that we will cross the sand layers. That is about the pile drivability. And then this is about the in-service conditions. In-service conditions, we will have a whatever here you can see in this figure. This is a top sides, let us say. Here you have only dead loads and live loads. Dead loads is nothing but the self weight of the structures and the self weight of the equipments, piping, all this, all equipments, anything, that and all will come in the dead loads. Live loads will come into the operating fluids, okay, and then any equipments which will be moving here and there, like some equipments will be coming in for with respect to maintenance and this kind of the things. Those called as those are all live loads. And and then in addition to that, then we will have a wind loads on the top sides. Then here on the jacket structure, we will have a wave and current loads. All these loads will transfer through the piles, and piles is how it will have a capacity is through the skin friction, not just the end bearing, but it will majoritarily skin friction, not based on the end bearing. So that is the philosophy. Here I want to highlight one more thing. If the jacket, if the piles are through the jacket leg, the jacket is just meant only to resist the wave and the environmental loads. Basically, it is not taking any of the topside load. Topside load will directly go through the piles only to the seabed. So this jacket is helping only in resisting the piles due to the environmental loads, because it is too much of length. So because of that, these jackets will be used. Okay. So the annulus between the jacket legs and piles will be grouted if required, but it is not a mandatory. But for the living quarter platforms, we will do grouting because of to reduce the time period. But for other platforms, it depends on the time periods. So basically what I mean to say is a jacket structure doesn't carry topsides weight unless unless if the piles are cut sleeves. If it is if the piles are not through the jacket leg, if it is somewhere over here, then the entire topside weight must go through the jacket and then transfer to the piles through the skirt sleeves. So this is a loadout for the topsides. Topsides, you can see that typical topsides here. This also either again similar to that by skidding or by trailer or by lift. By lift is very minimal, because in onshore we will not have such a big crane capacities like a 1,500 or 2,000 ton capacity. Cranes won't be available on the yard. So almost by lift is almost ruled out, mostly by either by skidding or by trailers only. So usually topsides weight ranges from wellhead platforms, it will ranges around 3 to 4,000 tons weight, whereas for the topsides process platforms it will go up to 20 to 25,000 tons also. The present project where I am working on it for Vietnam's project is a 25,000 tons topsides heavy weight. So that will be by the skidding only load out, even because trailers cannot take that much weight also. So that will be by skidded. And transportation same as a jacket. So all this roll, pitch, yaw, angular accelerations and the sway, surge, heave, linear accelerations will be considered in the transportation analysis and ensure that all members have been designed for that. And whatever the output comes, then that output will go to the sea fastening design and relays design and then barge strength checks and all these things. And in offshore, it will be installed by lift. If it is a small 3 to 4,000 tons, then it will be installed by derrick barges. You can see that here. This is a jacket already installed in the installed position. This is the top sides lifted from the cargo barge, and then it will be installed over here. This is the one sea fastenings, so from which it has been cut and removed, and then it will be installed onto the jacket. Jacket may be on the other side. And this is the float over. Float over is for if the top sides weight is too heavy, then we will transport it on the barge. And the barge will go inside the jacket. Here you can see this is not two jackets, it is a one jacket only. It is a shape is like that. Inside is this is a open area. So this barge will enter inside, and then what will happen after entering is they will ballast it. That means they will flood with the water these tanks inside the vessel, so that it will come down and the legs will sit exactly on all these positions. So that's how these heavy topsides will be installed. Probably I would share this one. This one float over, you can see here. This is the vessel transporting this is one of the project chevrons in Thailand. This is around 19,600 tons weight. We can see that here it is transported, and then this is the jacket, which is 8-legged structure. This is one wellhead platform which will be connected through the bridge from the once topsides is installed. So the tugboats will be there on all around on the tugboats will be there for the cargo barge. So the tugboat is pulling this one, and this will be guided, and the sides will be guiding. This front one will be pulling this one. The white one is a living quarters. Okay. So once this is a tugboat, you can see tugboat. You can see the rope also. You can see. So this is pulling this one, and then it is entering. Once it is entered, and it is now you can see that all the 8 legs are in the same position. Once it is this operation is very sensitive, because it has to, it is not steel to steel. There will be an elastomers there. It is called LMU, leg mating units. So that will have some capacity to absorb the impact loads as well. So that will be exactly, it will be like sensors will be there. Once it is all 8 legs are aligned, then the sensors will come into the control room on the barge. Then they will be start ballasting. Then once the ballasting is done, then it will be topsides will be supported on the jacket, and then the and then the cargo barge will be ballasted further. Then after that it will be retrieved out. So then the final welding will be happen between the jacket leg and the topside, like once it is installed. That's how the heavy topsides will be installed. So this is here, still the barge is there inside. Yeah, now it's gone. So this is after installation. Here it is, a still barge is there. Okay, going back to my other presentation. I'll close this. So platform installation, now we know how we are going to install this. Barge cranes, we have talked about it. The limitations on that, maximum is 4,000 tons. That is also very expensive, 4,000 tons. So if suppose top size weight is around say 6,000 tons, we don't want to go for float over because of the expensive. That option is very expensive. So in such case, what we will do is the top sides we will break into 2 or 3 modules. So what we will do is on the jacket structure, first we will build an module support frame, which is called MSF module support frame, which is a lighter in weight, like a 1,000 tons or 1,200 tons, something like that, which will be on top of that. It is like a big platform which will be kept on top of the jacket. Then over that, this entire deck, if it is say 6,000 tons, that will be divided into 3 components. Each will have like a 2,000 tons. Then each will be lifted and placed one after the next. So that is also one way we can install if it is at heavy top sides. Not necessary that we have to go with the float over only. And cathodic protection for the jackets. This usually this cathodic protection will be in the form of anodes, okay, zinc and aluminum bar casts around a steel, and the total number of anodes will be determined based on the so many parameters, C-state C resistivity and all these parameters. But typically the weight of the anodes will go at least 7% of the weight of the jacket. And in the splash zone, the jacket will be painted. So with additional wall thickness of around 12 mm, half inch. So that in the splash zone, we won't keep any anodes because there is no water there. So if water is not there, then this, if there is no water, then this anodes doesn't work, because the medium of conductivity is water for this anodes. So that's the reason splash zone will not have a water always. So we will have a protective coating system over there, and also with additional wall thickness of 12 mm for all the members, jacket, legs, braces, everything. So this we have seen this before in other presentation. Basically, how what are the types of loads, wave forces, wave and current, and how the loads will be transferred onto the piles, how the capacity of the piles is through the skin friction. If we go with a larger pile diameter, let us say if it is a 90 inch, then it with a pi d, the diameter, the surface area is bigger, then it will have a more skin friction. If it is, that is the reason we will go for a higher diameter. But the thing is that if you go for a higher diameter, then the jacket leg diameter will be more. And if jacket leg diameter will be more, then it will attract lot of wave and environmental loads. So if the water depth is too high only, then only we will go with scut piles and then with larger diameters. If the water depth is smaller, then we will go with piles through this one. But if the weight is too heavy, then we will go with the scut piles, even though if it is a shorter water depth. So structure design wise, as I mentioned before, the dead loads and live loads. Beside these 2 things, then environmental loads. Environmental loads is wind loads on the top sides, and then wave loads and current loads, and then earthquake is a different condition, earthquake loads, and then construction or installation loads. Installation loads means like a load out time during the breakout force, or racking loads, displacements, and transportation time during the transportation, this motion accelerations. During lifting time, the load path is different. During the in-place conditions, the load path is different, and during the lift condition, the load path is different. So that is one condition. And then during launch also, entire jacket load will be just concentrated at 2 points only. So that load path is different. So for all these scenarios, we will design the structure. And for accidental loads comes like a vessel impact, vessel impact is the one, and then dropped object. Dropped object is not very significant. Dropped object is nothing but if the crane is handling very heavy equipment from the cargo barge onto the topside, or from topsides to the cargo barge for any maintenance regions. If suppose it dropped, then that is, we will design it for dropped object protection also. So predominantly these offshore structures is governed by with the environmental loads, wave and current loads, jackets. Permanent loads, we have discussed about this, equipments and associated whatever it is on the platform, like a piping and HVAC, instrumentation, electrical, all these things. And then on the jacket, the additional is this wave environmental loads and hydrostatic collapse pressures, buoyancies, all these things. Operating live loads is drilling production facilities, living quarters, furnitures, life support systems, helicopters, heliport, consumable supplies, liquids, all these things. And forces generated during operation, like a drilling vessel mooring, crane operations, all these things also will be under live loads. And then the on the platform, the live loads is like a crew quarter, living quarters will be designed for it's not 5 kilonewton per meter square, sorry, it's typo, it's 2.5 kilonewton per meter square for living quarters. And for on the platform passageways, it will be designed for 5 kilonewton per meter square. And for the working areas, it is a 15 kilonewton per meter square, and laydown areas, it is a 25 kilonewton per meter square. It all depends again the material handling. Suppose we have a big compressors over there, and if it requires any maintenance, then we will have to transport the compressors from the wherever it is on the platform to a platform called a living laydown area. Within the platform, there will be on one corner, there will be a laydown area. So it has to travel all the way to the platform at one corner with the trolleys. So all that path has to be designed for a compressor loads. And then once it is placed on the laydown areas, then it will be lifted and loaded out onto the cargo vessel for maintenance. So all these conditions need to be considered in the design of the topsides. Wind loads act on the portion of the platform above the water level. So it will be majorly on the top sides, and wave loads will be on the above. Wave loads will be just above the water, MSL means sea level, and it depends on that the trough and crest also up to there. And then the currents will be below the splash zone majorly. So a lot of loads. For combinations, what we consider is a wind, wave, and currents. We will consider that, assume that it will act simultaneously, and the jacket will be designed. Suppose if it is a four-legged jacket, we will design it for waves, wind, and currents will be attacking on 0 degrees, 45, 90, 180, like that. So basically, we will try to see the maximum moment angle at which it will generate. So for that, it will be. And wind will be for the top size, we will consider it 1 minute sustained wind speeds combined with the normal and extreme waves. And sometimes like a sensitivity structures like a flare booms or bridges, which will be designed with the 3-second gusts. And the wave theories, the wave and current loads are usually the most important of all environmental loads. One of the other reason for using the tubular sections in the jacket is because the drag coefficients are less for the tubular sections. It will be 0.65, whereas if we use non-circular sections, then of course you can use see, tubulars means it is a circular hollow section, but we have a hollow sections in form of rectangular and square hollow sections also. But if we use them, then that will attract more wave loads. So we don't use them, though they generate the buoyancy, but they will attract more wave load, more drag loads. So that is the reason we go with the tubular loads, which will reduce drag forces. And computation of this wave forces is okay. I'll go to the next slide for that. So here is this we know that trough and crest and wave height and wavelength, all these things. And wave height, we will based on these parameters and based on the water depths, we will calculate which wave theory is applicable, like Steen's theory, Stokes, or Aries wave theory, whichever the wave theory is applicable, then we will use that wave theory. And using the Marison's equation, we will calculate the loading onto the each and every member. We will sum up all the forces and then normal stiffness analysis. But when it comes to the jacket, it will be a non-linear analysis because we will have a pile foundation also. So it will be considering the non-linear analysis, like when because of this environmental loads, whatever the platform moves, then again the pile soil interaction, it will apply the first initial position loads, and then it will apply the lateral movement, and then that will be transferred back to the pile foundation, then reversal. Like that is a non-linear analysis. We will use the Morrison equations because it's always most of the times the diameter of the member and ratio of the diameter of the member to the wavelength is less than 0.2. So that's why we use the Morrison equations. This is for the slender members. Sometimes it will, like I shown this gravity-based structures. Gravity-based structures is a big one. Like a length itself is around 30 meters, height by 20 meters, something like large volume bodies. There we will use a hydrodynamic compact structures. That is a different diffraction theory. That is, there it will be diffraction theory will be used for calculating the wave loads. But for fixed platforms, we will use this Morrison's equation for calculating the loads. So inertia forces proportion to the particle accelerations. So this is spectral earthquake loads. This is again earthquake. We will perform for two things. One is a strength level earthquake. Another one is a ductility level. The strength level will be for the elastic design. We will design it for the elastic, and whereas for the other one is inelastic response, the ductility level. So we will design for both and meet all the requirements as per the API guidelines. I'm not going in depth of this earthquake or fatigue analysis because it is a very big chapter. I don't think I can cover here. Ice and snow loads is also not in our region or in this major. These are mainly in Antarctic regions only, ice and snow loads. And temperature loads is basically in the flare booms only, where the temperatures will be very high. So because of the temperature, what will happen is the yield stress of the material or structural steel material will be reduced. So that will be considered, profile will be the temperature profile will be considered for designing these steel structures like flare booms and all those things. And the marine growth is one important factor. Marine growth is a significant, marine growth is, it will be formed on the jacket legs and braces and all those things. Over the years, it will have a heavy, thickness. So that will attract more environmental loads. And in addition to that, when we install the jacket, in the new jacket, when we install, the surface of the steel tubular is very smooth. So the drag coefficient for smooth is different. But over the years, when the marine growth forms, then that will become like a rough, very rough. So that time the coefficient, it is not only increasing the diameter of the member to attract the inertia and drag loads, but it also, the factor also will change for because of the roughness. That is one of the marine growth impact. So this we have discussed in other slide, how we will install and all those things. Except this first one, you can see that this is a construction sequence. During the construction also, this kind of the sequences and all we have to consider whether the members are capable, because each and every time the load path is changing here, right? So in all the scenarios, we have to design the structures. So construction sequence, that is. And the next one is a lift and appendings. Accidental loads, we have already discussed that. Accidental loads is collision with vessels, and even with the fire analysis or blast analysis, based on the risk study analysis, we will come up with a blast pressure. Based on the blast pressure, we will design the structure for those blast pressures for both elastic and ductility level also, and then we will see whichever members is very important. Those things we will be provided with the PFP, fireproof protection, so that will last for at least 1 hour or 1.5 hours, so that people can evacuate the platform by that time. That is the intent. It is not that to protect, but it will go, but at least people can survive. That is the intent. If you remember, around 10 years, I think, in Mumbai High, we had one accident in Mumbai high waters. One vessel went and hit on the risers, and then it got fire. Around, I think, 150 people got killed, ONGC people there. So special measures are normally taken to reduce the risk from accidental loads, like blast loads, fire, or even for the vessel impact, all these things. So in Mumbai High, just wanted to deviate the topic. Why it happened even after that measures have taken is they have installed one riser after the platform. After 10 years of the platform, they have installed one riser outside the jacket. Okay, but they did not provide any protection to that riser. So one of the supply boat came there, and it hit that riser. So because of that, so riser got damaged, and then all the oil exploded, and then it got fired. So entire platform got fired that time. These are the load combinations. Load combinations is basically operating conditions. Operating conditions means it will involve for the dead loads and environmental loads and live loads. That is the thing. And then for extreme cases, it will be only change in extreme cases is we will consider the 100-year or 1,000-year storm environmental loads. And both the cases we will do it for maximum live loads and minimum live loads, and also for the maximum water depth and minimum water depth. What is the maximum water depth and minimum water depth is? See, the water depth will be determined based on some based on a survey, which may vary by slightly, like a 1 meter or half a meter also. So even that also have an impact. So we will have to consider that maximum water depth and minimum water depth. And similarly for the maximum and minimum live loads also. Why we have to consider minimum live loads is because we need to check for the compression case also. If it is a environmental is a, if suppose 1,000 years, 10,000 years environmental case we are doing it, we have to do it with the minimum live loads and minimum dead loads. Minimum dead loads means with no contingencies. Dead loads is dead loads, you cannot reduce that, but with the zero contingencies on it. And live loads is the minimum live loads. And with that, with the 100-year, 1,000-year wave loads, environmental loads, if you consider it, we'll have to ensure that piles are okay with respect to tension also. So that is the reason we consider with the minimum live loads and minimum maximum water depth and all this kind of the cases. Structural analysis. The analytical model is used. I mean, it is a stiffness analysis. It's a standard stiffness analysis only. Only wherever required, we will go with a if it is a pile structure, then we will go with a nonlinear analysis. We'll build the soil profile also with the properties. Each and every layer we will build with the TZ curves. TZ curves is the skin friction curves. And lateral curves also will be there, and then end bearing curves also will be there. With all those things, we will perform the nonlinear analysis. So I'll share this presentation with coordinators, so he may be able to share this presentation with whoever is interested. The acceptance criteria for each and everything is there is an acceptance criteria for each and every element. Like suppose member stresses, we have a guidelines for API. For a joint check also, we have a guidelines. We have a member acceptance criteria for these things. For earthquake also we have in the same API, and for fatigue also we have many things, like in up to certain water depth is you must have a, suppose platform life is say 25 years, then we will have a factor of safety over the service life. Like say if it is 20 meters below the water depth, then the factor of safety is less. Then if it is much more than that, then factor of safety will be higher, like that. And wherever inspection is required, we will have to do it. We'll have to mention that inspection also. So usually operators will go for a inspection also. But usually, this lot of this fatigue analysis itself is a probabilistic analysis. The number of occurrences, okay, the number of occurrences and the wave height, period, all these things are probabilistic. So with over that, then again we are building the factor of safeties and all those things. That is the reason so far we have not seen any any incidences with respect to fatigue. Okay, with the codes available as of today. So with a lot of conservatism is there. So I don't see analysis is a very difficult, but it is not a governing. Only the nodes only will be governing. The giant nodes only will be governing. Otherwise, it is okay. So I think that's all my presentation. And some of the offshore standards what we use here is a DNV presentation, and then DNV standards we use, and then API is we use most of the times the API RP WSD. WSD is a working stress design. So this is the code which we use majorly, and then DNV guidelines also we use. BS codes we don't use it. Only the British offshore sector only will use those BS standards, and some references if you would like to. But nowadays, this presentation prepared a long time back, but nowadays you have a lot of things available on the YouTube or Google. That's all from my end. If you have any questions, then I am ready to
answer. Thank you, sir. Sir, if you allow, I will welcome the participants for questions and queries if you have. Yeah, I welcome all the participants. You can raise your queries, and Srinivas sir is there. Clear all your doubts. Yeah, sir. Actually, Dr. Tirupati Naidu has mentioned you in chat box. Sir, your presentation is specialized and rare.
Yeah.
Thank you, Tirupati Naidu, sir, for your feedback.
Thank you, sir. Thank you very much. In fact, when I joined this industry, I am also thrilled to see this. I don't know anything, but my seniors helped me to understand everything, and I learned from them. I'm thankful to everyone.
Sir, Dr. Tirupati Naidu is asked a question. What about cyclonic turbulence conditions?
Yeah, we will be having a cyclonic turbulence condition also in the environmental. We will consider the wave heights during cyclonic turbulence conditions are different, wave height and time period. So we will be considering those things.
Sir, it is a request from my side. Could you please share this PPT with us?
Sure. I will definitely share that one.
Thank you, sir.
Thank you.
Is there any questions to ask, or else we will share the feedback and we will come to the conclusion.
Okay, Raghubabu and Raghubabu Garu and Shashidhar Garu, I'm thankful for both of you for giving me an opportunity this one. And I don't know whether my guru is there here, Sudarshan Rao sir. I don't think he has joined.
Not here.
Yeah, not here. Yeah.
Shashidhar sir, are you there?
He's my, he taught me the structural analysis in the second year. And
actually, sir, just now only I came to know that you are the alumni of JNTU.
Yeah.
In the batch 1988 to 1992, I think so.
94, I
college batch.
94 passed out, yeah.
Just now I came to know about it, sir. We are very thankful to you, sir, for accepting our question. And really, you have given a deep insights of this knowledge. Actually, most of us are not aware about these offshore structures and how it will be designed. Really, we thrilled with your presentation, sir. I'm welcome all the participants. If you have any questions or if you wanna share your feedback with Sreenivasulu sir, you can please. You can unmute yourself and you can give your feedback. Right. Yogi, sir is there?
Yeah, I'm available.
Sir, 1 minute, sir. She's joining.
Sir, Professor Shashidhar is intended to talk with you, sir.
Okay, sir, no
problem. I know, sir, we are troubling you a lot, although you are busy.
Yeah. In fact, I spent only today afternoon I started this, and I could not find time to spend as I was traveling. I just reached Anantapur yesterday late night only.
Sorry, sir. Sorry for
No
troubling
problem at
you.
all. Yeah,
Uh, Actually, we have around 160 active participants across India, sir.
Sorry, I
Sir,
forgot to
good evening,
mention.
sir.
Sorry, I forgot to mention one more name. He's
Sir,
my friend. He's my friend, and he's in the committee as well, Mr. Sorry, Dr. Venkat Reddy.
yeah.
Because of him only we got connected. He's my friend.
Sir, good evening, sir. I'm Dr. GT Naidu, Chief. Your presentation is very well, sir. I think it reminds me my professor at IIT Chennai in ocean engineering.
Okay, sir.
This jacket and jacket structures 30 years back.
Okay, sir. Yeah.
Yeah, I'm very happy to listen from you again.
Actually, now my profession, I used to do these offshore platform designs and all those things, but last 10 years I'm into the new field. I mean, like in a more than 3 kilometers water depth. What we do, we cannot install any structures and no one can go there.
Yeah.
There it is it is subsea deep 3 kilometers water depth, 2 kilometers water depth and all. So
Yeah.
only with that in that kind of the systems I'm involved now actually. Structures.
How the process of soil exploration at the depth, sir? What is the
Soil
any?
exploration is there are, I mean, like reputed companies like Fugro and all. They will send they will collect the core samples from there. There are separate tools are there. I'm
Okay.
not very into that, but they will give us the all the soil properties. Cool.
Yeah. Professor Ganesh Babu taught me at that time this Jacob and Jacob structures. It is very familiar at that time. Now it is so many structures are coming. Thank you, sir. You are very
Thank you.
specialized, very exposed.
Nothing is special, sir. In fact, when I see Mr. Jithendra's presentation, it
Yeah.
really impressed me a lot. Really,
Yeah.
the way he presented and really drawed attention.
But Jitendra, I asked you some questions about recently Bihar. So many bridges are collapsed.
Yeah.
Every month one bridge. I do not know, but there is no time to talk with him. Okay. Yeah. Thank you very much, sir. Very nice.
Sir, we will provide his mail ID. You can contact him at any time through a mail.
Yeah.
Sir. Right. Anything else to talk with Sreenivasulu sir from audience? Yeah. If not, sir, I'm going to conclude this session. Once again, sir, I would like to thank you for accepting our invitation. Really, sir, you took us into a deep session. We are very happy that I also assure that all our participants have got the insights of offshore structures. Thank you very much, sir. Thank you for your time and expertise. Thank you very much, sir.
Thank you. It's my pleasure.
Yeah. Uh, Dear participants, I have shared the feedback links in the chat box for session 5 and session 6. Please fill the Google form in on or before 9:10. Okay. We will meet you tomorrow with new topics. Thank you, everyone. Good night. Once again, happy Merry Christmas.
Thank you.
Good night, sir. Thank you.
Good night.
Has everyone filled the Google form so that we can close the session? I request the participants to please fill the Google form. I request all the participants to please fill the Google form for today's session. Thank you all for joining the session. Let us meet tomorrow.
Thank you.